Ladies and gentlemen, welcome. On behalf of MyRailS project, it's a pleasure to open this workshop, metrology and measurement for an efficient electric railway system. This project, the aim of this workshop is to present the activities and results we have performed inside MyRailS project, Metrology for Smart Energy Management in Electric Railway System. It's a European project funded by Horizon 2020 program and by research program of Euramet, the consortium of European metrology institutes. The project started in 2017, and now, after 3 years and a half, we are in the end. We developed a lot of activities, measurements. I remember that this project is focused on metrology and measurements inside the European railway system. I'm not alone to moderate this workshop. I ask help to my friend, Engineer Donato Carillo. Now he is the General Secretary of CIFI, Collegio degli Ingegneri Ferroviari, and it was a pillar of the Italian railway system. So I give the floor to my friend Donato. He will speak in Italian. So if you want to listen the translation,
you have to click on interpretation and select the right language. So please, Donato, if you want to say.
Thank you, Domenico. Thank you. Buongiorno a tutti, buongiorno a tutti. Innanzitutto un saluto da parte del Collegio degli Ingegneri Ferroviari Italiani, che è vicinissimo a tutte le iniziative in cui si dissemina la conoscenza scientifica e le innovazioni ferroviarie. Vi porto il saluto del Presidente del CIFI, Gentile, e siamo onoratissimi di poter contribuire a questo progetto che ha visto impiegati, impegnati in prima linea tecnici di diverse realtà ferroviarie. Volevo ricordare a tutti che quest'anno, il 2021, è l'anno europeo delle ferrovie e ribadiamo praticamente come la ferrovia sia un mezzo sicuro, sostenibile e soprattutto innovativo. È la forza della ferrovia che ormai sta per compiere 200 anni.
And if after 200 years, the adaptability of the sector and the willingness to innovate, we're still able to thrive. On the 15th of December 2020, the European Parliament has voted the decision to make 2021 as the Railway European Year, with just 9 votes against and 2 abstentions. So an overwhelming majority of the European Parliament decided that 2021 will see a plethora of initiatives to the awareness on why the world railway system should be fostered. I would like also to remind us on how important it is to be aware on how to optimize our systems, and to be aware we need to measure correctly. One of the European Community goal is to reduce the emissions to accomplish the carbon neutral goal by 2050 and to halve our emissions by 2030. Behind this goal, we need to have plenty of innovation, research. We also need to implement solutions like hydrogen trains. We need to implement the energy saving that we will talk about today, and many other interesting activities. What can I add? The aim is to make the railway system as the main one. We need to move from road transport to railway transport. Today, we move 7% and 11% of passengers and goods. And of course, we want to improve. Now, I would like to remind ourselves how important railway was during this pandemic. We helped moving goods from China to Europe, and we were able to move more efficiently and time effectively goods from Asia, China towards Europe. In this way, railway has shown its capabilities. We will see a change in our sector, and this will allow us to foster the freedom of movement of people and goods. And we have shown that we are more cost and time efficient compared to other transport solutions. And that we will have to deal with industrial changes. Our sector stems from ideas implemented years ago. I remember during the Expo Railway, we were talking about energy meters, and this is a topic that is really thriving, and it's engaging with stakeholders. And we're dealing with problems concerning how much we're consuming, how we're consuming, how can we save, and how can we plan future consumption. It is fundamental to have a planning tool in order to deal with the energy market. During today, you'll hear what is new on this market. What are the highlights that will be trends over the course of the next few years, and what innovation can be introduced? I now leave the floor to Dr. Asinari as Scientific Director of the INRIM, and please, Dr. Engineer, please, you have the floor.
I think that we can switch to English. It's my Institute. And in particular, I will thank the colleagues from INRIM and all the partners of the MyRailS project organizing this very nice final workshop for their project. So I think that nice opportunity for us to introduce you briefly some highlights of Institute. I'm just waiting for my presentation that I prepared, and I'm asking for the control of the presentation that I still don't see on the screen. So I ask the supporting staff to upload mine. Otherwise, I can use.
Sorry, Pietro, you are the first, so.
No problem.
As
no problem.
usual, maybe there is a technical problem, and.
No problem. No. I can speak forever. I mean, as a scientific director, and of course also as a university professor, I can speak forever about nothing. So. But all the attendees may prefer to see some figures and numbers I prepared for in the institute. But I think that the topic it's extremely relevant, and also in the presentation you will see that I will definitely point out what is the vision of the institute that was recently prepared by our president, where the e-mobility in a very broad sense, and more specifically, this focus.
Now we are ready. Okay. We are ready for the presentation.
Good. Excellent. I still don't see it.
Just a moment. Maybe we need.
Now something is coming. Yes.
Okay.
Yes.
Okay. So you can take the control going in view options.
Okay. Yeah. I should have the rest now. It should be okay. Let me see if it works. I asked the control, but it seems that I can't.
You have to click once on the presentation and try to move.
Okay,
with arrows.
It works.
Okay.
It works.
Good.
Fantastic.
Very good.
Good. Thank you for this technical support. So I'm actually the scientific director of the institute, as already pointed out, and I'm also the full professor at Politecnico di Torino, which is the Technical University of Torino, with many topics, including also engineering for railway systems. So it's somehow pertinent, even though it's not my personal background. With this presentation, I like to give you, let's say, a few figures and numbers about INRIM, the National Metrology Institute, but also the Institute for Research in Metrology, that is very relevant since we are talking about an MPIR project. And in particular, I will focus on the vision document that we developed recently, that I was mentioning before, which is a sort of 10 years vision of where we want to go, and where you will see the topic relevant for this workshop perfectly fit in. And then also we'll mention a few ongoing activities that are pertinent for these topics. A few words about the Institute. First of all, we are organized in 3 divisions: Advanced Materials Metrology and Life Science, Applied Metrology and Engineering, Quantology and Nanotechnologies. So as you can see, there is a quite broad spectrum of activities. We are very proud to cover many different topics, even though, as you can imagine, it's becoming, of course, quite demanding nowadays, but we try our best, of course, and this is a merit of all the colleagues that are involved in these activities. The idea of these 3 divisions is not to be some sort of separate rooms, but they are just a sort of management tool that we use in order to follow properly different activities. So there are no strict barriers splitting the activities of the Institute. If you want, you can see on this slide more details. These behind these 3 divisions. So, for example, the Advanced Materials and Life Science which is very pertinent for this workshop, because Domenico is one of the organizers, belongs to this division more specific. You can see that there is electromagnetic fields and systems, which is extremely relevant for the topic of the workshop. But there is a general, of course, interest with regards to magnetism, spintronics, materials that are useful for supporting. And also there is, within the same division, also a branch about bioscience, let's say life science. So as you can see, the common ground is magnetism, but it can be explored under different point of view. So from a more applied point of view, as the one that we see today, including also more theoretical ones. And then we have another division, which is more focusing on applied metrology and engineering, both including mechanics and heat transfer. And finally, we have a division about quantum metrology and nanotechnology. You know, quantum is really a sort of rising star nowadays, checking all the European programs. It may seem something far away, but actually it's not. It's becoming really the underlying principle development of many new sensors. So our expectations, and also the European program expectation, is that there will be more and more sensors based on quantum principles. And this definitely will help to have a smaller sensor, a reliable one, taking into account this quantized property of quantum mechanics, and also maybe cheaper one that can be used in different applications. So we think that this is also relevant for other fields. So some achievements, just to have an idea, I tried in these 2 rows to present some of the, just few of the results we are very proud of. In the first row, it's report. There are some highlights from the metrological activities, which is very tied to the new SA, the new International System of Units that has been recently approved, but still has a long way to go before becoming, let's say, pervasive and filling all different applications. And also IRIM gave important contribution in establishing this new system of units. In particular, the 3 pictures that are reported there, they somehow present the efforts of the Institute with regards to the new definition of the mass by using measurements for the crystallography length, the space of silicium. And then there is our chamber for measuring the speed in rarefied gases, which is essential for redefining the Boltzmann constant. And finally, there is the cesium fountain, and this is the standard methodology for defining the second. But actually, there are also other activities ongoing, for example, for new kind of ytterbium atomic clocks that are very promising for redefining again the second future. In the second row, I also reported the publishing activity of the Institute. The Institute is quite active on top level journals, international journals. As you can see, few examples are reported there. So these are data from 2019, but actually, I mean, we are just collecting in these days a summary of the results achieved last year. So I will update soon this slide. Numbers, so we talk about 120 roughly researchers and technology. Then we have technical staff. Of course, for the activity of the Institute, technical staff is very important. That's why we have 110 technical staff supporting the labs, machinery, the procedures, the quality there. It's also to point out that we have a remarkable number of researchers in training. As a professor, I'm very happy about this because, of course, I believe that training and education is the key future, not only for developing technologies, but also for spreading the knowledge about technologies, and in particular, spreading the knowledge about metrology, because somehow metrology is sometimes considered a sort of essential tool, but not that well known. For example, even in the academic community, I can testify. So it's important to spread the knowledge about these remarkable activities. Our campus is pretty large, I would say. It's also nice. Unfortunately, today we cannot enjoy it, but definitely there is a very nice setup there. I'm sure there will be chances in the future for you to visit. We have 40 labs. So this is a rough estimate, because sometimes it's not that easy to split the different labs. To highlight once more the efforts of the Institute with regards to laboratories, of course, and then other numbers you can find on the slide. So what is our vision for the e-mobility, e-transport? So essentially, as common to many other strategic documents, the key point is the reduction of the transport emission. This is becoming more and more important, and of course there is an increase in public awareness with regards to this issue. For example, in Torino, we are aware of what are the consequences of having too high transport emissions, for example, and the two challenges or contribution for trying to promote this reduction goes along these two lines: the accurate estimate of the energy. And of course, in the university, I belongs to the energy department, so I'm very, very, very keen on the energy, of course, but also on the evaluation of the impact introduced by the new technologies in order to have a better optimized management of the power flow. This was what also Domenico was pointed out in the opening welcome. And I'm very proud to say that this kind of vision is very aligned with the 10-year vision prepared by our president and approved by the Institute last year, where you can see there is an explicit quote in this document where we say that the energy conversion and distribution and e-transport application will deserve particular interest, not only by our institute, we believe, but also by other authorities, and also we hope from the private sectors. I just mentioned that local region in Piedmont, there are relevant, I would say, industrial investments with regards to train and to the train technologies and business. So just the two ongoing activities. One is, of course, MyRailS. We are very proud to be coordinating as an institute. And also I want to mention MySieve, which is another MPIC project about methodology for inductive charging of electric vehicles. So just to mention that this vision started a long way ago, even before the formal document was approved. And these projects are two very good examples of efforts done by the Institute. Of course, I think they are two excellent examples of the capabilities of the Institute, of course, thanks to the colleagues that put efforts into it. In particular, Domenico worked very hard on them. So the engineering policy is, of course, to see this e-transportation as part of the efforts of the Institute with regards to the European Green Deal. We believe very much in the Green Deal approach of the Commission, and I will say, if I can, that our president in particular is very, very keen on the Green Deal. He has a strong sensitivity with regards to these topics, and he's trying to let's say, put more and more efforts and collecting resources on this policy. And that's all. So I just there was also another slides about the MySieve project event that maybe will be pointed out later on, and that may be an option to also advertise a little bit the audience about this further event, yes, in case they may be interested. But I want just to close my comment thanking all of you, the organizer, the colleagues, those that are attending this workshop, and underline the importance of the topic, and trying to see the spread of the results you achieved in a scientific and industrial community. Unfortunately, I have to apologize in advance that today I have other commitments. As you can imagine, as scientific director, my life is pretty busy. But I will try to be with you as much as I can. And then, unfortunately, I will leave you, and I will leave you in good hands, in the Domenico hands. Thank you very much to everybody.
Thank you, Pietro, very much for this overview of INRIM. Thank you, Carillo, for the previous speech. Very interesting. Now, let me say, before starting with the first session, I would like to mention all the partner of MyRailS that I didn't say before. We have 16 partners, for sure, with the coordinator, the Spanish Metrology Institute, Fundación para el Fomento de la Innovación Industrial and del COE, LNI, the French Metrology Institute, METAS, Institute from Switzerland, the Czech Metrology Institute, CMA, VSL, the Metrology Institute from Netherlands, the National Physical Laboratory, NPL, Metrology Institute from UK. We have many industrial partners that allows us to perform any on-site measurement campaign. RFI, the Italian manager of the infrastructure, of the railway infrastructure, Trenitalia, the main Italian railway company, Metro de Madrid, the manager of the management of Metro de Madrid network, Hitachi Rail, and ASTM, a small enterprise from Switzerland. And we have also the contribution, the big contribution from universities and research institute, Università della Campania, Luigi Vanvitelli, Rainium, a French research institute on railway topic, Strathclyde University from UK. Okay. So we can start with the first session. The first session is will present the activities related to the calibration, to the development of setup for the calibration of the energy measurement functions. That is the measurement chain for the estimation of the energy
la stima dell'energia consumata e utilizzata dai treni.
So I can give the
floor quindi do la parola
Jorge Rovira.
A Jorge Rovira.
Please, Jorge, you can
quindi Jorge,
the control of the presentation.
La parola è tua e puoi prendere il controllo della presentazione.
You have to unmute the microphone.
Okay, thank you, Domenico. Thank you. Hello to everyone. I am Jorge Rovira from FFII LECOE. I work on research projects at the official high voltage laboratory of Spain, and I will present the calibration of energy measurement systems under AC distorted waveforms. First of all, I would like to give you some indications about the context. Trains are often supplied by distorted voltage and current. In this way, the energy measurement system must be calibrated under the real working conditions. For this purpose, calibration setups and procedures have been developed under this framework. This calibration setup consists in an AC50 power source, 15 kilovolts for 16.7 Hz or 25 kilovolts for 50 Hz and 500 amperes with harmonic contents up to 5 kilohertz. Here you can see the electric scheme and the measuring systems, and the low voltage instrumentation. For instance, the full multimeters for voltage and current. Here is the laboratory calibration, some pictures. The first picture on the right shows the multimeters and the source. In the middle, you can see the current transformer, which induces high current into the current loop. Here, the reference current sensor is placed. The reference current sensor is the blue one. On the left, the high voltage is injected and measured in the bar where both voltage and current waveform are superimposed. The voltage is measured by the reference divider, and the energy measurement system is also installed in the bar. In the middle, you can see. Okay, now we are going to see a video of the calibration setup.
Ora vedremo un video del setup di calibrazione. Il setup di calibrazione può
Common AC railway systems, 25 kilovolts for 50 Hz and 15 kilovolts for 16.7 Hz. The maximum current is 500 amperes and 5 kilohertz for the frequency content. The generation system is based on a 50 power source. You can see the two low voltage sources. A voltage regulator for sinusoidal waveforms, and a programmable voltage source for waveforms containing harmonics. This source is used for feeding the voltage transformer or the current transformer depending on the needed. This source is controlled by software. Additionally, a synchronization module is used to get the same frequency for both voltage and current signals. Measuring instruments are disposed here. Two digital multimeters are used for recording both voltage and current wave shape in a synchronized way. This oscilloscope shows an example of the waveforms recorded. Now we can see the current transformer. This transformer induces the high current into the current loop. The current loop is a high voltage cable that provides electrical insulation to the current sensor. The reference current sensor is disposed into the current loop. In the middle of the current loop, the energy measurement system under calibration is installed. Finally, this bar is used for high voltage injection using voltage transformers. And also for the voltage measurement. This divider is used as reference voltage sensor.
Okay. Well, we have the
Quindi
setup
abbiamo
for
appena visto
laboratory
come è
calibrations, and now we are going to see the setup for onboard calibrations, that it is for onboard situations. Here in the picture, you can see the calibration setup for onboard calibrations. A new disposition has been designed and some mechanical components have been assembled. For instance, the aluminum bars that you see are part of the current loop and connect the setup to the bushings of the train. The bushings are shown in the picture on the middle, and bushings of the train are connected as well to the energy measurement system. Well, now I am going to present calibration procedure based on the EN 5463 standard. The calibration points of the graph are applied and the following tests are carried out. First of all, the accuracy test of harmonic content. Then, accuracy test with harmonics in the voltage. These harmonics contents are applied in the voltage waveform. Please take note that some harmonics have been included from real measurements in railway systems. These measurements have been presented in this project. The third is the accuracy test with harmonics in the current circuit. In the current circuit, yes, sorry. These harmonics contents are applied in the current waveform. For this test, also taking into account the real measurements in the railway systems that Railenium and some partners has presented us. And finally, the accuracy test of the influence of harmonics in the current circuits. For this test, the waveform on the right is applied. This waveform is presented in the standard and it's called like phase 5 current waveform. Finally, the result evaluation is out by the software, by the calculation of energy and errors. And at least for more information, I have included the publication related to this work. Okay, thank you very much to all.
Thank you. Thank you, Jorge. Okay, I think that now we can continue the talk on the calibration of energy measurement function under AC waveforms with the contribution of Daniela Istrate from LNE. And then we have time for question and answer. Just a moment, they upload the presentation. Is appearing.
Thank you, Domenico.
Thank you.
Hello, everybody. Thank you for attending this work. My presentation comes to complete Jorge presentation and also to outline setup that we developed at LNE in the framework of this project. So. What should I do? I am trying
you have to go
switch.
Okay.
Yes. So this is a slide to present the context. As you know, there is the 2008 in the European community, and that is why, with the aim of establishing a single European railway area, the necessity to to measure correctly the consumed energy appears. So the standard that Jorge named, 50463-2, asks to verify, to check the accuracy of energy measurement functions. And so to answer to these requirements, we develop a setup that will be presented in video, isn't it? That started. And it presents the setup of the
This setup works up to 25 kilovolt and 50 hertz voltage and up to 500 current with harmonic going up to 5 kilohertz harmonics. The calibration accuracy varies from 0.1% for active power for sinusoidal conditions up to 0.5% for active power in distorted conditions. Managing the generated signal is very important in metrology since it allows guaranteed calibration accuracy. The generator provides two low-level voltages that are synchronized by a 10 MHz signal. This allows the implementation of a phase-locked loop that controls the phase between generated voltage and current. For the current, numerically generated waveform is provided by the generator and amplified by the transconductance amplifier, which has a 20 ampere per volt gain. The current is amplified twice by the injection current transformer through its ratio. Therefore, the current flows into the device under test is 200 times higher than the initially generated voltage. The 50 Hz low-level voltage is amplified once by the audio amplifier that generates up to 100 volt. This voltage is the input voltage of a step-up potential transformer, allowing to reach 25 kilovolt potential. This high potential is applied to the device under test. The second part of the calibration setup represents the reference measurement system. It is composed of voltage, respectively current sensors, digitizers, and data treatment algorithm to determine the requested quantities. The whole acquisition is triggered by 10 MHz signal that synchronizes the generation part. The voltage reference transducer is the step-down instrument transformer with a ratio of 30 kilovolt to 100 volt. The current reference transducer is an inductive type of current monitor with 5 MHz bandwidth and 50 millivolt per amps transfer coefficient. As it can be noticed, the reference current sensor is placed at more than 50 centimeters distance from the return cable and from the device under test, avoiding thus any crosstalk effects. Two traceable resistive dividers are used to adapt the level of voltages for the 1 volt range of the digital multimeters in order to take advantage of the high accuracy and stability of this range. All these components are calibrated and traceable to the LNE national standards.
Yes. So, thank you. I complete this presentation with some slides dedicated to the software. And I would like to go to the next slide and to complete what was said in the movie. Yeah, it's okay. I would say that this setup is able to be used. We can use this setup either with correction implemented or without. Implemented correction means that the disturbances that the setup might introduce are identified and corrected. And this allows to have the harmonic of 5 kilohertz as we want, with the amplitude we want. Therefore, the device under test is seeing the waveform we would like to do. So for the sampling frequency has to be adapted to the fundamental signal, if it is 6.7 or 50 hertz. And we compute this sampling frequency, taking into account the fundamental of the measured signal, the number of points, and the number per cycle, and the number of recorded periods. In our case is 5 cycles. The software drives the multimeters, pilot the data acquisition, treats data, and perform mathematical analysis and computation. So once we start an acquisition, a package of 5 cycles are recorded, and several packages are recorded that might be stopped at as the user would like. So the output of the software are the RMS values of voltage, current, the phase displacement, which is voltage and current, the active power, and of course, since there are multiple acquisition of, we can have the standard deviation of each of these electric quantities. Also, we can see the waveform for voltage, for current, and their frequency spectra. This work, the setup was used to calibrate a device under test. And here is just an example of a calibration point. We noticed that the device under test, so the correction obtained are 0.2%, which is okay with respect with the standard and with the fact that this device was not designed to work up to 5 kilohertz, less more. Therefore, and the whole measurement has an uncertainty budget, so we can measure active power generated by sinusoidal voltage and current with 0.1% uncertainty. And for distorted waveforms, we have a 0.5% uncertainty related to our reference measurement system. As Jorge mentioned, we published together with our Spanish colleagues and our Czech colleagues, and some of these publications are listed here. That's it. Thank you for your attention.
Thank you. Thank you very much, Daniela, and thank you, Jorge, for the nice presentation and very clear videos. Thank you. So we have now 5 minutes for question and answers. So I will ask to the Zoom audience if is there any question or even consideration. Maybe Carillo.
Più che domanda, un commento. Ringrazio Jorge e Daniela.
I would like to thank both Jorge and Daniela, because I felt young again, because I used to take measurements and I could see that you are very focused on the right use of the standards and you want to comply with European directives. So you're working within a coordinated system. And also, I can see that you're very focused on the accuracy of measurements. So I can go back to my initial words.
Veramente interessante i vostri interventi. Grazie.
Thank you, Carillo. Is there any other question or consideration? Otherwise,
question for Daniela. I would like to ask you which has been the biggest challenge you have to face
arranges this setup.
Oh, sorry, Domenico, but I didn't get
I
all.
repeat.
Yes.
I repeat the question. I ask.
Probably an audio. The question is which has been the challenges you face during
The design and the arrangement of the setup on meteorological point of view.
You are asking us?
The problems you have to face in the arrangement, if you have problems in the arrangement, in the design and the arrangement of the setup in order to generate
Oh, yes. I will
maybe
yes,
maybe.
I will speak for current because Eleni
Yes.
dealt with current, and then I will
Yes.
let Jorge answering for voltage because they first deal with generation of voltage with harmonics. So for current, yes, there is a working point to be found for the transformer, for the injection current transformer. And this is a kind of compromise between the way of controlling. I mean, we can pilot this with the current transformer with current or with voltage. We can control it in, so we choose the current way of controlling because it's a kind of linear magnetic material. And let's say we have a direct answer proportional with the current injected. We tried this, and but the impedance of the setup of the secondary counts, and it is seen in the primary, and it has not to be too much. So also the ratio of the of this injection current transformer has to be well chosen and well designed. So this was our approach. The magnetic materials that compose the injection current transformer are compact and with nanocrystalline particles, so they allow to reach this 5 kilohertz signal without saturation and high amplitude of current, of course.
Thank you very much, Daniela.
Yes,
Okay,
for FFFII was the same issue. The main problem is the magnetic materials of the transformer, which they don't have a very good behavior at higher frequencies. So at 5 kilohertz, we can reach only a few percent of the frequency, of the fundamental frequency. So for harmonics.
Thank you. Yes, because the core is to generate not only 50 hertz, but even harmonics.
Yes, and the selection of this transformer was the main issue at the beginning.
Okay, thank you very much. And now let's move on DC. And so the setup for the calibration of the energy measurement function for DC railway system. I give the floor to Davide Signorino from INRIM.
Good morning, everyone. Can you hear me?
Few seconds. Yes, very well.
Okay,
you can take the control of the presentation.
Okay.
Okay, good.
So, good morning, everyone. I'm Davide Signorino, and I work at INRIM with Domenico Giordano. Thanks to this project, I am a PhD candidate in meteorology at Politecnico di Torino, and today I will show
al
you...
dottorato del Tecnico di Torino.
Yes.
Yeah.
Okay.
Yes, there is for just a few seconds there is the translation, but maybe now you can continue.
Okay.
In a right way.
And today I will present you a calibration system for DC power or energy measurement chain. Let's start from the state of the art. Until 2019, the billing for the energy consumption was not made on the actual dissipation of the energy by the train, but on the basis of several factors, such as the length of the route, the type of the train, and in this way, as you can imagine, it's not a word that a good way, an ecological way of driving the train, but compared to a more dissipative one. So for this reason and for the interoperability among the different railway system in the European area, the European Commission requires that by 2019, all the trains shall be equipped with an energy measurement function that from now on we call it the EMF, and the performances and the measurement accuracy of this device has to be assessed and periodically re-verified. In order to get the best performances from the meteorological point of view, we think that this type of devices, measurement devices, should be tested under the actual operating conditions. So we think we need to improve our calibration setup and our procedure, which go beyond to new procedures that go beyond the well-known procedures developed for the pure continuous regimes. The last thing that we have to consider is that today there is no meteorological capability for the energy or power measuring in the DC. So today, for calibrating a system that measures the power or energy in DC, we have a two-step calibration, we can say. In the first step, there is the calibration of the voltage channel. In the second step, a calibration of the current channel. As you can imagine, this type of approach cannot be used for our EMF because this device needed the simultaneous presence of both voltage and current signal for properly working. So what we want to propose today, we have realized a setup calibration that can calibrate this combined voltage and current transducer and can calibrate the energy measurement function for DC train installation. This reference system is able to generate a voltage up to 5 kV and a current up to 2.5 kiloamps in simultaneous condition. So a phantom power up to 12 megawatts. We will explain very soon what is a phantom power, because for sure we don't want to generate the power dissipated by a train for the characterization of its measurement device. And we do this with a good accuracy under stationary condition of 250 ppm. This reference system is also capable of emulating the waveform that we get in other measurement campaign, real measurement campaign within the MyRailS project. And we can test the EMF under this condition with an accuracy of 0.1%. For its structure, this generation system can be used in laboratory for the EMF calibration, but even on board for the re-verification, of the EMF. Now you see an image that has been taken directly from the standard that you see written above that define what actually is an EMF. It is an onboard instrumentation that has a current measurement function, a voltage measurement function, and an energy calculation function. So with our calibration setup, we want to, let's say, calibrate these three functions. Here you see the EMF that we used for our preliminary test. It's a commercial device. It can be used under several railway systems in DC from 750 volt to 3 kilovolt. Its transducers are very good for this operation because for both voltage and current we have an accuracy class of 0.5. And the outputs of this EMF are two currents. One that is proportional to the voltage and goes from 0 to 20 milliamps, and one that is proportional to the current that goes from -20 to 20 milliamps. Here now we see a preliminary setup, a preliminary scheme of what on how we realized our calibration setup. This first image is a representation, a very basic representation of the EMF. We modeled the very simplified model. We modeled the current measurement with the series shunt and the voltage measurement with the parallel divider. So as I told you before, we don't want to waste the power dissipated by a train for the calibration of the EMF. So we use the phantom power approach. This phantom power approach consists in the generation of voltage and current in different way. So for doing this, we need a controlled current amplifier and a controlled voltage amplifier. For measuring the voltage and the current that we are applying on this EMF, we use a current reference standard and a voltage reference standard. Of course, in this way, this configuration is not applicable to the system because all the elements are supplied directly from the grid. In this way, the elements that are present, let's say, on the current loop, work at a common mode voltage that is imposed by the voltage amplifier. And this voltage is greater than the insulation voltage admitted for the element on the current loop. For this, we use an insulation transformer. There is a transformer that as a one-on-one ratio, but the secondary of this transformer, we connect the ground terminal not at the real ground, but at the high voltage node that you see highlighted in the slide. So with the two asterisks, you see marked all the elements that are supplied through the insulation transformer. But with one asterisk, you see the elements that are supplied directly from the grid. Now we need the controller. Actually, there are two identical controllers that are composed in this way. We have an arbitrary waveform generator for the control of the controlled voltage amplifier or the current amplifier. We have a data acquisition system for measuring all the signals provided not only by the reference transducer, but for acquiring the signal that are provided by the EMF under test. And at last, we have a GPS module that is fundamental for this type of operation because we need the synchronization not only between the two arbitrary waveform generators for handling the time delay between the generation, the voltage and current, but we need a synchronization between the acquisition system channels. At last, we even use two shunt resistors because, as I told you before, usually the EMF as output has two currents. So we need to translate them into voltages. Now I will, everything is connected as controlled by a remote PC with fiber optic connection for the safety of the operator. Now I will show you a very brief video where I'm talking about the instrumentation that I used for this setup. Okay, I don't know if you see the video.
No. Okay.
Here we are in high voltage laboratory at INRIM. Here we perform calibration and research activity. And what you see behind me, it's the station for the calibration of the energy measurement functions. Here you see an example of an energy measurement function. It's called JD, and it's provided by MyRailS. This device implements two functions, the voltage measurement function and the current measurement function. The outputs of this device are two currents, one that is proportional to the voltage and one that is proportional to the current. For measuring these two currents, we use that two standard resistors from Guideline. They have an overall accuracy lower than 10 ppm in a bandwidth from 0 to 10 kilohertz. After this, we apply the voltage to the EMF thanks to the voltage amplifier that you see over there. It's a track voltage amplifier. It can generate a maximum voltage up to 30 kilovolt in a bandwidth from DC to 2.5 kilohertz. Actually, it has a wider band for low voltage signals. And the signal that has to be amplified by this amplifier is provided by the arbitrary waveform generator that is inside this controller. It's an NI 5421 arbitrary waveform generator. It can generate a voltage in the range -12 plus 12 volt with 16-bit resolution and the sampling frequency up to 80 megahertz. In this controller, implemented thanks to chassis NI PXI, we have also the GPS module. This GPS allows us to synchronize this controller with the other controller that is for the generation of the current signal. So this module disciplines the internal clock at 10 megahertz thanks to the GPS signal. This other module is the acquisition module. It's called NI4462. Has 4 channels, 4 independent channels with 24-bit resolution and a maximum sample rate of 208 kilohertz. The last one module that we use for safety reason is the module that allows us to control all the equipment thanks to the fiber optic cables with the fiber optic connections. For measuring the voltage that we are applying to this EMF, we use this voltage standard with this voltage divider. It's an ohmic capacitive divider, and it's designed for medium voltage. The project and the realization of this divider, it's all made in INRIM. So we use it as a standard reference, even for other applications. This is all for what concerns the voltage generation. So one thing that we have to consider is that it's all supplied by the grid. So the voltage, the supply voltage is referenced to the ground. On this other side, we see all the instrumentation that is supplied by that insulation transformers. This is a transformer with ratio 1:1 and has an insulation voltage of 6 kilovolt. Thanks to this transformer, we can supply all the, let's say, current loop, and especially these 2 DC power amplifier that can generate up to 1.2 kiloamps for each. For measuring the current that is provided to the EMF, we use this reference current standard. It's a LEM ETZ Ultra Stub that has an overall accuracy lower than 12 ppm and a bandwidth from DC to 500 kilohertz. The output of these instruments is still a current, so we need to convert it in a voltage, and we do it thanks to that Tinsley shunt resistor, that even in this case we have a lower accuracy lower than 10 ppm. So it's important to remark that we use the fiber optic connection for the safety of the operator, because in this way he can work properly behind the grid, so without any risks for the operation. Okay, now here we have a list of all the capabilities of our setup. We can generate, as you see, a voltage over 5 kV. We can generate a current of up to 2.5 kiloamps, so we could generate a phantom power over 12 megawatts. As you can see, if we use an insulated rack for all the current or the elements of the current loop, we can perform this measurement not only in lab, but even directly on the train. So we can do the re-verification of the EMF on board the train. Thanks to the software, we can calibrate not only the meters with the analog output, but even those one with the digital outputs. And thanks to the arbitrary waveform generator, we can emulate the real operating condition, emulating the signals that we get in the other measurement campaigns. And in the same way, we can generate a high number of different tests. Here we see the how we perform the power and the energy calculation and how we evaluate the error of an EMF under test. We define the power as the product of the mean voltage multiplied by the mean current. And the interval on which the mean is done is called aperture time, delta T, and can go from 5 to 20 milliseconds. So the energy has been calculated as the product of this aperture time multiplied by the sum of all the power contribution in time analysis. We define a ratio error for energy as the ratio between the difference of the energy measured by the device under test minus the energy measured by our reference transducer, all divided by the energy measured by our reference transducers. Now we see a preliminary test that we have done in the stationary conditions for deciding which value we have to generate. We refers to the European normative 50163 railway application supply voltages and traction system that define the over voltage limit curve. As we can see, is defined by the exponential formula starting from Umax3 to Umax2. And for the quantities Umax1, Umax2, and Umax3, for the 3 kilovolt line, this value are equal to 3.6, 3.9, and 5.07 kilovolt. So as the image describes, for example, the limit of whatever voltage for a time duration of 1 second could be max Umax2, 3.9 kilovolt. For a time that is greater than 120 seconds, we can have at least 3.6 kilovolt. So we decided to use these three voltages, 3 kilovolt, 3.6 kilovolt, and 3.9 kilovolt. And for each of these voltage, we tried, use the value for the current that are 100 ampere, 300 ampere, and 1 kiloampere. So as you can see, as we expected, the results are very good when the current, so the power is high. Things get a little worse, but however, under 1% when the current's value are lower. So these are the standard, the static testing standard static condition. Now we see the test in dynamic condition. We replicate the Susa to Torino part of the Susa to Torino route. As you can see on the left side, we have the y-axis for the voltages that you see in red and in black, the voltages that we get from our reference transducer and the transducer under test. And on the Y scale that is posted on the right, we see the current that are measured in blue with our reference transducer and in green with the transducer under test. We see here that the thing slightly changes, but we have to underline the fact that we have tried the device under test, not the entire EMF, but just with the voltage calculation function and the current measurement function. So these errors are just related to the transducer. This means that with the energy calculation, with the implementation of the energy calculation function, we can get better results. So now I know that the representation of number is wrong, but what I want to show you here is that we have tried to measure the energy and the error related, the ratio error of the energy in 3 different ways. And all the ways conduct to the same results, we can say, because in first place we have done the ratio error of the energy calculated as the product of the all voltage and all the current integrated in all the time analysis. In second case, we use an aperture time of 5 milliseconds, and in third case, we use an aperture time of 20 milliseconds. As you can see, the results are slightly different respect to the stationary condition test. So in conclusion, we can say that we have realized the phantom power generator for the calibration of energy measurement function for several railway systems in DC from 750 volt to 3 kilovolt. This generation system can be used not only of DMF, and in the end we can see that some preliminary tests in dynamic condition have been performed, but this demonstrates the necessity of the definition of new type of test that assess the metrological performances of the energy measurement system under the actual operating condition. So thank you very much for your attention, and that's all.
Thank you, Davide, for this nice presentation. I think that now we have to jump on the debate. We arrange a debate at the end of each session. I have a few slides that I think will trigger the debate on the topic related to the calibration of energy measurement functions. So as you can see, the MyRailS contribution is the development of a measurement of a setup for the reference generation of phantom power and so phantom energy. So the idea is to reproduce in the lab and also on board train the real condition experienced by the energy measurement chain on site. So generating harmonic at 50 Hertz with the high voltage 50 Hertz component and generating DC signal with real behavior for what concerns voltage and current. So, ok, just a moment.
Ok, solo un momento. Lasciate che...
So, considering this, this contribution to go beyond the state of the art, I'm asking which is the contribution of MyRailS, for example, related to the improvement of the standard 5463-2 that deals with the energy measurement functions and its accuracy. So considering the previous state of the art, let me say, the energy measurement function accuracy was defined as the quadratic sum of three components. The accuracy associated with the voltage and the current transducers, and the uncertainty associated with the energy calculation function. Now it has been fixed, this methodology to evaluate, estimate the accuracy related to the energy measurement functions. But we are considering these three quantities that are actually tolerance intervals as stochastic variables. Okay, this simplify the calibration of the energy measurement function because you can separately considering each block of the chain for the measurement. MyRailS develop facilities that allows the calibration of the entire chain. So I think we can go over this definition we can provide a more rigorous approach in the estimation of the uncertainty associated with the energy measurement function. There is an example in the standard that allows to the evaluation of the uncertainty, but for us, let me say, metrologists, there is not a rigorous implementation of the GUM, the Guide for Expression of Uncertainty. In fact, there is confusion between definition of errors and uncertainties. The errors is something that you can know and you have to correct. The uncertainty is the residual that you cannot correct. So we can propose even simpler examples that allows people to estimate the uncertainty associated with the energy calculation functions. Thanks to the setup developed, we can suggest possible procedures and the setup for the periodic re-verification of the energy measurement function. So directly on board the train, it's important, the re-verification, because, for example, in DC, the offset can affect the energy measurement, and the offset can vary with time. So it's important periodically to verify the accuracy of the energy measurement function. And going beyond the state of the art, we can propose a set of power behavior in the time. I mean, a set of signals in AC and in DC that allows the estimation of the accuracy under real dynamic condition. Because in the end, what we want to know is the accuracy under real condition. And finally, this is the question: a European Measuring Instrument Directive for Railway World. Today, the infrastructure manager has to divide the energy bill among companies operating on its network on the base of the real consumption of each train. Like the administrator of a building, that the building has only a common energy meter. The economic exchanges associated with the purchase and sale of electricity for residential, commercial, and light industrial use is defined by the European Directive, the MID, well-known Directive 2014. And so each one of us can buy the energy from any operator on the free energy market. The question is, could a locomotive owner purchase or pays energy directly on the energy market? A necessary condition to allow this could be a directive MID specific for railway world. So this is the possible contribution that can comes from MyRailS. If is there any question or consideration regarding this point of view, you can raise the hand for people inside Zoom. You can contribute. Of course, this is a point of view of the metrologist that works on this topic. But we don't know if it's a real need, in particular for what concern
Can you hear me?
Yes?
Yes, morning. I am Andrea Gatti. I was.
Hi, Andrea.
I'm part of the working group of Senelec working group in charge of developing the standard and
yeah.
Question of the.
Good morning.
Morning. And the question of the measurement instrument directive the application of the MID directive to the EMS was one of the first issues that we raised when we started the working on it. And at the end, at the moment, you are right. There is no, the MID is not applicable to the EMS because the MID aims a completely different kind of devices. So this is one of the main questions, the main topics. The other part is that the MID do not cover the railways environment. So there is no cover the requirement coming from the different environment coming in the railway, typical of the railways environment, like EMC, vibration, operating temperature, and so on.
Yes.
This is leave a big open point is the assessment of the system from the methodological point of view. So we have explained, the previous persons explain how it's possible technically to certify, to verify the accuracy and the behavior of the equipment. I think it's still an open point. The complete assessment of the equipment from the meteorological point of view. Yes. This is one of the, I think, one of the open points, not only the one. The other one is the interoperability between the onboard equipment and the data collecting system and the settlement system on the ground side. But it's not out. It's not inside the
yes. Yes, I know that.
Of this meeting.
Yes. Thank you very much, Andrea, for this consideration. If is there anyone consideration, comment, or even a question regarding the previous presentation? I would like to point out another interesting thing regarding the methodology described by the standard to evaluate the accuracy of the energy measurement function. That is the root mean square of the sum of the quadratic component of the uncertainty of each block of the chain. For example, considering this, what's happened if we add inside the energy calculation function correction factors that compensate the errors introduced by the transducers. I can build a transducer with not so good accuracy. It's precise, for example, but it's not accurate. So I can compensate in the electronic that perform the computation, the accuracy. So if you consider each element, okay, and you make the summation, you have a better accuracy. But if you consider the whole system, you could increase the accuracy, saving money, because to develop a transducer accurately as a cost, to implement the correction inside the energy calculation function is cheaper. This is a consideration. Okay. Daniele Gallo raise hand, but if you can give the floor to Daniele. Daniele, you can
okay,
unmute.
Thank you. I have some trouble about hand, but anyway, I want just we are a little late, so
yes.
I want just a general comment about the importance of accuracy in measurement of power and energy, because in my opinion, having accurate measurement is the first step to save energy. If you know properly how you use energy, you can choose to improve your energy usage. So you can only buy a correct, a sound knowledge about energy is possible to define energy saving strategy. So the importance of effort of Meteorological Institute in measuring energy better and better is strategic from energy saving path.
Yes, I agree. Okay, thank you, Daniele, for this important consideration. So I don't see any. Daniela.
Yes,
please.
thank you, because you speak about compensate the sensor deficiency, let's say, and we worked on this indeed, and just I want to say that it is a work that it is worthy to do, because we will of course have a better accuracy of the calibration system, and we will trust more what we see, I would say, but it has to be done concerning the setup. I mean, it depends on the setup. Implementing this compensation, it is a work that asks time and setup characterization.
Yes.
And, yes, we did it for our setup, but for depend on the control way of generating the fictive power.
Thank you, Daniela, for this consideration. So I don't see any other raised hand or a comment in the chat. So I think we can have the first break for a coffee. Okay. So see you after 10 minutes. So let me say 11:15. 1 minute more. See you. And don't please don't go out of Zoom. You can switch off the camera, mute the microphone, but please stay in Zoom. See you later. Okay, let's continue the workshop with the second session, power quality in AC and DC railway systems. So now we have the first presentation of the second session. The presentation is by Peter Davis from NPL, and the title is The Power Quality Measurement in the AC Bologna Substation. Please, Peter.
Thank you, Domenico. Can you all hear me?
Yes, yes.
That's great.
Very well.
Thank you very much. So yes, as Domenico welcomed me, I'm Peter Davis from MPL in the United Kingdom. I'm here to talk about some power quality measurements that we undertook in Italy last year, and the equipment is still installed, so we're still taking some measurements now. So is this working? Yes. So in this talk, we're going to have a bit of a talk first about power quality. So this is the first talk in this section about power quality. So I'd like to give a brief overview of that. And then following on from that, I shall talk about the installation. So what equipment we installed in Italy, the location and the technology of that. We'll have a bit of a talk through the results that we took. So some of the example data. So the device we used spat out some sample data, but also could do fundamental and harmonics. And then after that, obviously, there's some post-processing of the results. So looking at power and other power quality metrics. And then we're finishing with a small bit, which was just a potential resonance that maybe we spotted, which was another sideline to this project, but might be of interest as well. So if we go forwards, then what exactly are we talking about in terms of power quality? So we want to, first of all, think about voltage dips and swells. And we also want to talk about maybe the harmonic content of our signal, so how much the waveform's distorted. In a normal power quality sense, we might also talk about the frequency of the system. This is obviously outside of the control of the railway network, but it is an important power quality metric. We might talk about power factor as well, so how well the power factor of the system is being controlled. This is a question of efficiency as well as, I guess, resonance as well, and then resonances too. So what exactly were we looking to do initially on this project? So we were wanting to find a location where we could do a power quality measurement for a reasonably long time in a single substation, which was quite secure. INRIM and their partners RFI had a few different sites that were optional, and one of them that looked very interesting was this site in Modena. So this is on the Bologna to Milano line, and it has these 4 sections of track which it looks at, which it powers from the Modena substation. And we were looking at just one section of track. It's the 27 kilometers north of Modena up to Milan that we're looking at. And we were looking for a network which had sufficient trains running through it that we wouldn't necessarily have to wait that long between them and maybe have 2 trains on the track at the same time, but a not so complicated network topography that would be confusing. So this is a reasonably straight bit of track. There's a 1 T point which isn't normally used, and there's a point which is commonly empty or closed. So if we go forward to the next slide. So this is the substation arrangement at this substation. So the substations, all the high-speed rail network in this section of Italy, they have the RFI owns its own 132 kilovolt network, and this 132 kilovolt network in turn drives the 25 kV feeders and catenaries on the train, which drive the trains. So there are a pair of 132 to 25 kV transformers, and then from the 25 kV bus bars, these in turn go through and gets distributed to the 4 sections of line, so north and south from the substation, and either going to or from Milan and Bologna. So for these measurements, we took the voltages of both the catenary feeder and separate neutrals for both of those, though they're probably connected to the same location. And similarly, on the currents, we put Rogowski coils around the secondaries of the current circuits. So it wasn't possible to split open the secondaries of the CTs, and the ideal obviously would be to add a shunt in. However, the Rogowski coil permits at least some measurement in this with a wider frequency band than maybe putting a CT over the secondary of the CT. So as we then installed one of these, a digitizer instrument. So the digitizer instrument that we installed was an NPL homemade digitizer. Generally, our equipment is lab-based, but these versions have been slightly hardened for field-based applications. They are GPS synchronized because part of this project, the intention had been to also install a second measurement on a train. So they came with this GPS capability. And into this, we took both the voltage and current measurements. They fed in, and we varied our sampling rate either at 25.6 kilohertz or 20.48 kilohertz. So that kind of varies whether you get your 512 samples per cycle or 4,096 samples per 10 cycle. We fed in the Rogowski coils, had their own integrators built into them. So we didn't have to worry about integration, and they just fed into 1 volt channels, and the voltages were fed into 110 volt channels. We attached just a normal laptop to this, which was for the logging and did quite a lot of data processing on site. So if you imagine doing six continuous FFTs, then that requires quite a large amount of computational power. So that was necessary. And we had a modem which provided remote access back in the UK. So we could reset, change our algorithms if necessary, change our sampling frequencies, and just generally control the equipment. And then a hard drive. So I think we had a 3 terabyte hard drive installed. If you can imagine, once again, that sampling at 25.6 kilohertz, you start to collect gigabytes and gigabytes of data just in a day. So we had to decide what was the best way to deal with this and how we were going to either select relevant data or just pick specific sample data that was of interest. So going forwards from that, this is some of the example data that we got from the system. So the data itself coming out enabled just fundamental values that we could calculate. So here is the top left is an example of some fundamental data taken in February last year. So we can see that over this morning period rush, when you might expect to see a lot of trains, the voltage actually increases during this time. This could be a presumption that tap changes on the network continually control the voltage to make sure the voltage is stable during it, rather than when you expect a higher load would draw it down. And similarly, we also have harmonic data, which is also split straight out of the system. So we can see the variety of which harmonics are most prevalent. And so in this case, the 5th harmonic seems to be the most prevalent, and then which of these are caused from either background events, so they're present all the way through the night, or which ones start to increase or decrease when the trains start to run. So this is also from February 2020. The obvious interest in power quality data from last year was that the network was not average from March onwards. As we'd say in the UK. There was a substantial reduction in train traffic. There was a substantial reduction in passengers. This caused some problems in terms of what would be a normal network for us to look at. But I think we managed to capture some of the interest or some of the things of value. The downside of the benefit actually of having such a quiet system was it felt that RFI was doing a lot more maintenance than would be expected. And quite regularly, the network would be switched on and off. and you'd see these lovely inrush currents into and out of the system, which enables us to characterize what the potential impedance of the network was better. And this was best viewed through raw data. So the second set here of data we've got at the bottom is raw data. This is taken from August last year. And the one on the left is voltage and the one on the right is current. And we get the catenary and feeder voltage, which obviously opposing each other by 180 degrees, and the catenary and feeder currents, which are similarly opposed but slightly different magnitudes. So because of the tightness of the installation in the connection, some of the Rogowski coils, we weren't sure whether they were operating to their maximum capability, and we're not sure whether we saw an imbalance continuously over time was actually more to do with the sensors than the actual network itself. So those were the data that we could just take as a raw values, which were spat out from our digitizer and software. However, there would be some other interesting metrics that we could do with those. So as well as the voltage and current, we obviously had the phase angle between them. And this permitted power and reactive power to be plotted across this same section of line. So this is going back to February last year again. We're looking at the variety of whether you can identify the signature of what a train would look like in this network as it rolled through the system. So we get these increases in power and these periods of braking, and whether in turn these could have been mapped to certain geographic locations on the network. So this section of line isn't particularly hilly, but there are some bends which might require extra power when accelerating or braking through, or stations which might require stopping at. And then similarly, we could look at histogram data. So looking at what exactly is the expansions, or what are the limits of the catenary total harmonic distortion, and whether this is within the actual standards, what we should be saying in terms of how far it deviates. And predominantly, we were not seeing particularly high total harmonic distortions at all on this network. So there was no, of the number of samples that we taken, so we didn't see much in the way of extrapolation much out of 2%, which is really good for a 25 kV network. Similarly, if we wanted to compare total harmonic distortion voltage against active power, the question would be, as current is drawn, would total harmonic distortion increase? So in which case you're saying your train on your line, how much is the interference from the train on the line increasing the total harmonic distortion of voltage? And it didn't really seem to have a slight, there was no significant impact. It felt, you can see there are almost these three levels here. So at 0 active power, you get all the range of total harmonic distortion, but actually when you're drawing 8 megawatts, you generally have a pretty low total harmonic distortion present. And the last metric on this slide is looking at the power factor of the network. And so one of the best ways to plot this is looking at power factor, but versus the active power. So as the active power is in the either exceptionally high or a low start, so kind of when you're very much drawing or sinking current to your network, you have a very high power factor, which indicates that very little energy is being lost at that point. You're not sticking it into reactive power, so that's really useful. I guess the interest is in how sharp the corners are, up at 1 and down at -1, but I think the boundaries we have there are about plus and minus 95%. So most of that is outside of the region. So if we go back to this point in the February the 28th, another example set of data we have is looking at the background harmonics that we produced, or that we measured. So we can see the variety of each of these, the odd harmonics early on, so the 3rd, the 5th, the 7th, the 11th to 13th, the 25th, 29th and 31st. So you can see all of those, and equally you can see a nice event happening around 528, which causes this smearing between them. So there's always interest what exactly these events are which cause the smearing. And similarly, we can look at the line voltage distributions. So what are the catenary voltages, and if we histogram those plots as well, where did the likelihood of the voltage lies? So we can see here that actually within this sample here that we have 200, within basically 95% of the values are in 200 volt region, which shows there isn't that much in the way of a catenary voltage distribution. It's really quite tight together. Similarly, the other metric that we looked at was how quickly the voltage stepped. So if you measured the value on one step, so another like a 20 millisecond window, and you looked at it on the next 200 millisecond window, what was the maximum voltage step in those times? And very infrequently was the maximum voltage step more than 20 volts. So that was also a nice way to say stability was occurring on the network. So the final thing I'd like to have a show is that of a potential resonance that we found. So one of the intended parts of this project was that we would have our substation installation, which we did, and that we would have a installation on a train. So that would have enabled the synchronous voltage and power measurement to be done both on the train and on the network simultaneously. And as the train ran through this section of network, we would have been able to keep voltage and current from both sides. This would have enabled us to have a in-depth understanding of kind of maybe resonances and frequencies and how the impedance of the line changed as the train went down it. However, because of the virus, this wasn't actually possible to do a train installation during last year. So we had to leave it up to a bit more modeling than we initially intended to see whether we could find any resonances on the grid. One of the potential locations we found for a resonance was just under 10 kilohertz, which, as you can appreciate, our sampling equipment is 20 to 25 kilohertz. So we're at the complete and utter edge of the Nyquist of what our sampling equipment maybe could take. But one of the things we did find was we actually did find a potential 9 to 10 kilohertz resonance on some of our data. And this is an example slide of that, showing that as the spectrum changes, so we've split this up into 5 200 millisecond windows, and early on, there is none of this, there is nothing visible in this, about just under 10 kilohertz. But as we get closer to 10 kilohertz, as we get closer to the middle window, sorry, this 10 kilohertz spike increases and then drops off again. And it's very difficult to see under other parts of the voltage waveform, but if you look at the catenary voltage just at the top, you can almost see this rippling, which is present. So it would have been really good if we could have had the train measurement to verify this, but it shows that actually, if this is pushing our equipment's capability, that we haven't really found any resonances much below 10 kilohertz, which if anything is a positive thing for the train network. So that wraps up my chat. I hope we've had an interesting few slides on power quality, what power quality is, and the measurement installation we completed in Modena, some of the data we've taken out of that, and if anyone has any questions, please let me know. Thank you very much.
Thank you, Peter. Is there any question? I think just to continue, we can collect the question and answer in the end of the power quality in AC railway systems.
Thank you.
We can continue and then. So the next presentation is power quality analysis in AC railway system by Ilion Seferi, University of Strathclyde. Hello, Ilion. Unmute your microphone.
Hello, Domenico. Thank you.
Hello. Take the control of the.
Yes. Okay. Hello, everyone. This is Ilion Seferi from Strathclyde University in Glasgow. Today, I'm going to give a presentation about the power quality analysis in AC railway systems within the context of MyRailS project. In this presentation, I am going to cover the motivation behind this work, and then we'll continue with the analysis of voltage interruption, voltage dips and swell, voltage and current harmonics that are recorded in the railway networks of European countries. And then we'll conclude my presentation giving some useful recommendations in the conclusion section of this presentation. So railway electrical networks are characterized by peculiar power quality phenomena because trains are interact with overhead contact line, with traction substations, and with other trains within the same power supply system. And they exchange power during acceleration, coasting, and then during regenerative braking. This condition can give rise to short-term power quality disturbances that are different from power quality disturbances observed in transmission and distribution grids. So the first question is to understand by evaluation if power quality methods defined in IEC 61000-4-30 are appropriate enough for accurate characterization of AC railway systems. And secondly, all these power quality disturbances need to be better understood, better quantified, and also properly classified. Oh, sorry. One of these power quality disturbances that is not properly characterized by the standardized method is the supply voltage interruptions. Voltage interruptions in railway systems, in AC traction systems, are caused by the network configuration characteristics employing phase separation sections or neutral sections to reduce the imbalance introduced in the three-phase power supply system. So in the graph on the left-hand side, in the plot, it is presented the train, which when it passes through these neutral sections, voltage interruption at the pantograph level of the locomotive is observed, and this is presented on the right-hand side of the slide. It is obvious that this standard cannot discriminate this kind of interruptions from other voltage interruptions due to other factors, for example, due to faults in the system. So, an improved estimation technique for voltage interruption discrimination is needed in AC traction systems of 25 kV that is presented in the next slide of this presentation. Sorry. So the time behavior of the voltage and current before the train enters these phase separation sections is presented on the plot. As we can see, the voltage is still constant and has not changed, but the current is reduced to zero before the train enters the phase separation section in order to avoid arcing. Later on, voltage will be zero as well, because either the pantograph can be lowered or the circuit breaker of the locomotive can be switched off. So the new technique considers voltage RMS and current RMS evaluated over one cycle, and then it checks if the voltage magnitude falls below a certain threshold, obviously the threshold of the voltage interruption. And if this is true, the current magnitude of the previous cycles is checked. If this current magnitude is lower than, is close to zero, these voltage interruptions are attributed to phase separation sections. Otherwise, voltage interruptions are attributed to other factors. So this new technique obviously allows a better understanding of the phenomena and, of course, improved classification of the ambient for statistical analysis. Due to traction load variability, short variation in voltage magnitudes are observed in AC traction systems of 25 kV, 50 Hz. So dips and swells of shorter than 1 cycle are not properly characterized by the method defined in the standard. So methods using shorter calculation intervals are needed for closer tracking of the dynamics of the phenomena, and also to better understand the dips and swell, and also to better classify these events. So in such a context, we have considered methods based on evaluation of dips and swells on half cycle and 1 cycle in order to understand the effect that window size has on the measurement results in terms of accuracy and time duration characteristics of the events. So the plots indicate a voltage swell and a voltage dip evaluated over respectively half a cycle and 1 cycle by the proposed techniques. And as we can see, the voltage, the differences in voltage magnitude are obvious, whereas in terms of time duration, voltage swells and voltage dips of time duration shorter than 1 cycle are required to categorize themselves in integer number of cycles or 1 cycle, whereas characterization over half a cycle for the time duration of the event is more accurate by a factor of 2. So since the accuracy is improved, also the classification of the event for statistical analysis is improved. For example, the voltage swell presented is not considered as a voltage swell if it would have been evaluated over 1 cycle, but it is considered as a voltage swell if it is evaluated over half a cycle. So clearly, the method using shorter window size to evaluate the phenomena produce much more accurate results in terms of time duration for the voltage dips as well, and also in terms of their accuracy. Regarding the harmonics, it is well known that AC traction systems are characterized by significant level of voltage and current harmonics, which are also time varying in nature due to change of the operational mode of the train. Such a variability for most of the significant voltage and current harmonics recorded during a train journey is presented in the graph shown in the slide. As we can see, voltage certain harmonics can have significant magnitudes in voltage and also in current. So the main point with the harmonics is the fact that in the network, power quality analyzers are widely used to evaluate the harmonic content of the network, and based on these results, mitigation techniques are proposed. So the processing technique used proposed by the standard due to the processing technique proposed by the standard because of the aggregation algorithms that are required to aggregate the measurement results, introduce a significant smoothing effect that makes all the time varying components to be underestimated. So again, we have considered that shorter aggregation times intervals are required for PQ measurement instruments to offer more accurate evaluation of harmonic emission levels, and also to dynamically track the harmonic change over the time in these networks. So the application accuracy of the standardized method is evaluated with different time aggregation intervals to understand their effect. A comparison is presented in both figures for one of the harmonics and the THD evaluated over 10 cycles as proposed by the standardized method, but aggregated over different time aggregation intervals. As we can see, differences of more than 10% exist between measurement results evaluated over 10 cycles and measurement results evaluated over 10 cycles but aggregated over 150 cycles. So in order to reduce these differences, we have proposed a 50-cycle time aggregation interval for the aggregation of harmonics and TSD in order to provide more accurate results. And of course, this will lead to a better understanding of their negative effects like overheating and so on in railway networks. At the end, we'll also have power quality instruments, more accurate for statistical definition of EMC levels. So to summarize, in this presentation, we have proposed an enhanced estimation technique for voltage interruption that potentially can improve the understanding of the phenomena and also its classification. It has also been shown that a window size of half a cycle can produce more accurate results for voltage dips and voltage swells and also for their time duration. And this is useful for event classification according to EN 50160 standard. The new aggregation interval that we have proposed, it is obvious that outperforms the 150 cycle aggregation intervals proposed by the standard. And this is a recommendation for future power quality rail instruments to use these recommendations. Okay. This is all by my side. Thank you very much for your attention.
Thank you to you, Hillian, for this clear presentation and the contribution in the measurement of IC power quality. Now let's move on the last presentation of this subsection for AC power quality. The next presentation is harmonic power, presented by Andrea Mariscotti, ASTM and Università di Genova. Okay, hi Andrea.
Hi, ciao Domenico, grazie. So thank you and thanks to everyone for joining this workshop. I am taking the control. Okay.
Yes, you have to take the control. Click on the slide.
Yes.
And,
so this work regards in two words the harmonic power. That means what is the amount of power that is brought along by harmonic components? Because so far we have seen power quality issues, and what is relevant for power consumption and energy consumption is the amount of power, active or reactive, we should say non-active power, that is that characterizes the harmonics of the specific rolling stock or of the network, because of course there is a mix of the two. The questions are, are put here black and white. So it is clear that we want to understand if the amount of active power is relevant, and of course this harmonic active power will increase the total active power. And the same can be said for the reactive power in terms of reactive power, properly said, and distortion power. And of course, the increase of reactive power causes an increase of losses indirectly because of the increase of the total current and the RMS of the current that flows in the system. Just at a glance, we can define all the quantities that we need starting from time domain expressions. I don't want to go into the details. You have the voltage on the left, the current on the right, and you can perform a very, let's say, quick multiplication to get the instantaneous power. And then on the left, we have the active power expression, and on the right, we have the, let's say, reactive power. But as you see, I might say that the reactive power, if you include harmonic terms, is more complex than the fundamental reactive power, because we have the, let's say, the properly said reactive power at the harmonic H, where H is the order of the harmonic. But we have also the distortion power. The last line includes a term for the DC component of the voltage and the current that, focusing on AC railways, can be ruled out. So let's assume that the DC components are zero. Maybe they are not zero during transients, but they are normally zero. So for those who are not familiar with the composition of the harmonics, if we take a very simple sketch of a spectrum of the voltage and the current, when we combine the two, we get active power components for harmonics that are calculated directly from the RMS of the single component, and then they are, of course, all referred to an ideal DC frequency, so that they can be summed all together arithmetically, and they increase the fundamental active power. For the, let's say, reactive power, we have a mix, because the multiplication of the frequency of one component in the voltage and one component in the current gives, let's say, a rate of components up to this value that is the maximum attainable by the mix of the two highest order terms here. As you see, as we said, we have reactive and distortion, and the total non-active power is expressed here. As you see, the composition is by summation in quadrature, so as RMS, not as an arithmetic summation. Of course, this is the total apparent power that, let's say, is immediately known as soon as we know the RMS values. So when we begin focusing on harmonic power quantities, we should, let's say, put some points on the table for the following discussion. So one thing that is interesting is what is the behavior of the active power pH during traction and braking. There are differences. Maybe the internal sources are different as behavior with respect to the external sources of the traction network, and so on. Of course, the active and reactive power, let's call it reactive power, at the harmonic H, they are interrelated, and they change values during time, leading to something that we could call the displacement factor at the harmonic H. The total harmonic non-active power, NT, is an interesting quantity, because it includes all the terms that are, let's say, not producing active power, but they increase the flow of current, so indirectly the losses, as we said. And then, of course, when we are speaking of active and reactive power at harmonics, we should always keep in mind that it is interesting if they are relevant in terms of amplitude. So we should always weight the active power and the reactive power at harmonic age or over a frequency interval with respect to the fundamental quantities. Of course, the first question regarding what does the active power with respect to traction and braking is interesting also because it's one of the most popular methods for the identification of harmonic sources. If I pull harmonic power, I am an harmonic source at that frequency. But there is a long discussion in the scientific, let's say, literature regarding the reliability of this indication, and this was one of the byproducts of the study. So just to keep, just to let's say, have a glance at what happens during a train run. We have a profile. This is Switzerland, so 16.7 hertz system, and the loco is a Siemens RE460. As you see, the profiles are going up and down in terms of, I mean, they are positive and negative because we have tractioning and braking. The reactive power is not that much with respect to the active power because there are limitations to the reactive power that is drawn by a running stock. And here on the right, top of the page, you see a snapshot of the frequency behavior for the, let's say, the most interesting frequency interval here, where all the relevant harmonics are, let's say, popping up. In this case, we see that we have, this is a graph of the intensity. This is a time frequency plot of the values of the intensity of the harmonics. And you see that we have some steady marks here. This is the full cardan converter on board of the locomotive. And there are some cases of transients, as we have seen already in the past presentations. As you see, in some cases, there are some intervals where the intensity is very low and almost all the harmonics disappear. If we go to consider the details, we can, let's say, first of all, consider what is the behavior of the active power, the harmonic active power, distinguishing between absorbed positive entering the rolling stock and regenerated or negative or leaving the rolling stock. In this case, this is a better representation of the previous graph, the previous picture. And as you see, there is a zoom of 500 seconds with respect to the previous one, where we can see that we have tractioning and braking, and then tractioning and then braking. And this is the speed in black. As you see, we have some components here around the frequency of the full quadrant converter, the traction converter. And then we have low order harmonics. Low order harmonics are everywhere, not only because a piece of rolling stock may absorb these low order harmonics because they have maybe some rectifier or something like that operating at low frequency, but because there is a pre-existing distortion on the supply network. So what is interesting here is that we have a red third harmonic corresponding to the traction, and it's highly correlated because it's blue when we have braking, and then again red in this case. The third harmonic is something that is peculiar of the 16.7 hertz because the third harmonic of the 16.7 is 50. And so we have the third harmonic as a byproduct of the let's say, characteristic transfer function of the transformer, but also because we have auxiliaries on board operating at 50 hertz, not at 16.7. So it's a peculiar behavior. As you see, we can say that this third harmonic is a good indicator because it follows the operation of the rolling stock. So we can say that it's generated by the rolling stock. There are some low order harmonics that are almost always blue, or they change in an opposite fashion with respect to the traction and braking. In this case, if they do like that, they might be indicators. If they don't follow the, let's say, traction and braking sequence, they are not good candidates for being harmonic indicators. The same is repeated here for Germany. The train is an ICE with a peculiar, is one of the two ICE used for tests. So it's the onboard converter is a little bit different from the commercial versions. And as you see, it's an old train, and there is a lot of pollution in the low frequency range, mixed between the network and the converter of the rolling stock of this item of rolling stock. As you see here, there are other harmonics caused by external rolling stock because they are always red, so they don't depend on the operating profile of this piece of rolling stock. We can, of course, as I said, we can think of the active and reactive power at the specific harmonic H as we do at the fundamental. So we can think of the displacement factor as a way to show if there is a correlation and if there is a, let's say, a coherent behavior with respect to maybe tractioning and braking, but of course coasting and cruising and so on. In this slide and the next one, I have just concentrated the traction and braking for some of the harmonics. As you see, we have some chaotic behavior when the harmonics are not caused by the rolling stock, and then we have some, let's say, coherent behavior like this one when the harmonic is caused by a rolling stock. That doesn't mean that it's ours. We can say that it's not ours because the angle doesn't change when we pass from traction to braking. So using graphical techniques for interpretation of the data, we can, so clustering and other things like those, we can use this kind of representation to classify the harmonic sources and recognize which one is the, let's say, is the culprit. The same can be done for France. This is a system with 50 hertz supply, and the train was a TGV DESI. These measurements, by the way, they refer to past measurement campaign. They were not performed in MyRailS. It was a European project that was carried out during 2007, 2008. The name of the project is Breakcom. As you see, the behavior is quite different, and we can recognize some low-order harmonics of the DESI because they are quite correlated here, and they lose the correlation here. And they are, so we can understand that they are caused by the tractioning of the unit. There are some dots here because during a braking, there is no full braking. The typical driving style is braking and then a little bit of acceleration and tractioning to keep the speed at a let's say, desired or prescribed level. One objection might be, okay, you have focused on power, but normally when working with power frequency drives, we focus on current and sometimes the voltage and the current can be displayed in a XY fashion that is called Lissajous trajectory or Lissajous diagram. Why you don't use this, or can we understand if there is some information, let's say, using the data in this way, so forgetting for a while of power and going to the current. If you see, all the diagrams are circular, of course, because there is a phase of rotation. These diagrams, they plot the real and the real here and the imaginary part of the current. But we can say that some of these diagrams, they are saying something. Because if you see the colors for the various levels of exploitation of the rolling stock, so the fundamental current, the intensity of fundamental current, you can see that there are some diagrams going from the internal part of the diagram to the external one. So we have, let's say, a monotonic or a coherent behavior with respect to the current absorption. That means that there is information here saying that this harmonic plane is characterizing the rolling stock, and indeed it is, because we know that these harmonics are the characteristic ones of the four-quadrant converter. So there is a confirmation, of course, that because we know our piece of rolling stock in this case. Taking all together the active power, so because we are focused on the active power at some of the harmonics, but taking all the entire active power that is absorbed by the rolling stock, we can calculate what is the weight of the active power with respect to the fundamental power. Of course, this can be done for frequency intervals, just to keep the information compact enough to have a meaningful graph, but of course, distinguishing between very low harmonics, intermediate harmonics, and high frequency harmonics, or high frequency, the highest frequency that we have considered in this graph. As you see, the 800 hertz of the full quadrant converter, they are here in the yellow. The purple is an interval that is not characterized by anything inside the converter, and this short interval contains the third harmonic and some low order harmonic. As you see, the lion's share here is for the 0-150 hertz interval, and the yellow one is also relevant more than the purple one because it contains the active power of the harmonic of the full quadrant converter. The values are in some cases interesting, and these values are occurring when the absorbed power is very low. So the P1 is low and the harmonics, they prevail. That doesn't mean that this is relevant for the energy consumption because these intervals are counting less than the other ones with full traction. Of course, we can consider also the correlation of the active power, and of course, we can do it also for the reactive power with respect to the drawn power P1 in a different way. So displaying something like a statistical distribution, of course, using dBs because the representation is more compact compared to the previous one that had a huge vertical scale. As you see, the low order harmonics are relevant, and when the power is also relevant, above 500 kilowatts, the values are in these ranges. So they become something that should be considered, because 1% of something that is very huge, the energy bill or the power absorbed, the instantaneous power, is something that is worth of being considered. For the harmonics at higher frequency, you see that they are marginally relevant with respect to the, if we consider the active power. We will see that the reactive power is more relevant and can be, let's say, an issue for the increased power losses, of course, not directly, but indirectly. As I said, if we calculate the absorbed energy for the four areas that are, let's say, sigmatized here, and they are defined in the 5463-2 standard, we can see at a snapshot on the left for the 16.7 hertz and on the right for the 50 hertz system, that the 16.7 hertz system is more, let's say, polluted, or the harmonic power is more relevant simply because this is a mixed traffic system. This line is the Zurich Brick line where there are several items of rolling stock from different companies all traveling back and forth. In this case, this is the high-speed line in Italy that is not so heavily utilized. In this case, the rolling stock is also more modern, so the distortion is much less. Similar results for France with the old DZ are very, very close to the Swiss case, Switzerland. In this case, you see that the impact of active power is not a big number always for the energy consumption, except for this 0.25. So we might say that at worst, we can expect active power carried by the harmonics around a fraction of % of the total energy. Of course, reactive power is a completely different scenario, because the reactive power, the total reactive power, so the non-active power in reality, is more than doubled if we consider the harmonic terms. And this is relevant, because even if the losses are just a few percent of this reactive power, we are speaking of doubling or 3 times or 6 times in this case the total non-active power without considering the harmonics. So as a conclusion, we may say that after, let's say, I might say a thorough evaluation of these terms, we can say that the active energy, let's call it active energy, as it is said in the 5463-2, is affected by this fraction if we consider the harmonic active power. But the reactive energy, and so apologies for using reactive next to energy, is much more, let's say, involved, and it's more complex and is more affected by the harmonics of the traction system, almost the same order of magnitude of the fundamental. So as a last caveat, we should remember that the active and the active terms, they are highly dependent on the characteristics of the rolling stock. Your rolling stock that you are measuring and the other ones that are circulating on the same supply section. So thank you for the attention, and I just put some references for further reading if you're interested in that.
Thank you, Andrea, for this complete presentation.
Information on European countries. Okay, Donato, now as a comment.
Alcuni commenti, alcune considerazioni.
Just a moment. If you want to activate the translation, you have to move on the upper part with the button interpretation, and you can select English.
Ok. Alcune considerazioni che partono soprattutto dall'illustrazione, dalla presentazione di Mari Scotti. Allora, la questione delle armoniche è importantissima perché sostanzialmente
because in the energy production during traction, harmonics are produced, especially in the case of 15 with the 16 and 2/3. In the case of industrial frequency, harmonies are managed, but there are issues connected to the filters of the rolling stock, and this has an impact on signaling tools. So the presentations we've just listened to that measure and characterize harmonies are absolutely vital and deserve a lot of attention on top of further work that will enable us to provide the stakeholders with data that will allow them to improve the output of their qualities when it comes to the impact on the train's path.
There is a problem with my microphone. Maybe now is okay. Okay. There is a question from a YouTube chat from Francisco Jose Gonzalez from Renfe. He asked about if we deal with in MyRailS on methodologies to compensate the harmonics. I have to say that this is out of our objective. Our main objective is to provide methodologies to measure the harmonic pollution, which is the first step, which is, and to provide reliability to the figure we are going to measure, we are going to provide. And this is the first step, very useful for the designers that has to design filters and techniques to compensate the harmonic content. So now, is there any question from the audience?
Domenico, may I say
Yeah.
just a thing for, let's say, 45 seconds?
Yes.
The sizing, the design of harmonic filters is quite complicated, because in reality, we are focused on energy consumption, power consumption, and harmonics. But harmonic filters, normally, they have to be designed also for the interference to the signaling. So, yes, start my video. So the problem normally is that the sizing of the harmonic filter is dictated by the limit masks. And there is a new limit mask that is, freshly brewed, was 2 years ago. And now there is another quite interesting and complex project in Italy for the, let's say, joining of the characteristics or the specifications for the old DC line and the new 50 Hertz line. That is a huge project that will take also this into account. So the tolerable amount of harmonics in the various scenarios.
Okay, thank you. Thank you. There are no other questions. So we can jump on next subsection, the Halloween power quality in the sea railway system. I have to give the floor to myself because I will present arc events at pantograph, a reliable way to detect them. So I ask to upload. Okay, I'll take control. Request. Okay. Outline. I will provide example of arc events. Before I will describe the measurement campaign we have performed in Italy that allows us to collect a huge amount of data sampled at 50 kilohertz and to perform that allows us to perform the analysis to develop the methodology to detect the arc events. We also performed the laboratory experiments in order to understand the typology of arc voltage that occurs when we have an arc between two sliding contacts. I'll show you the collection of arc events we found in a railway and metro systems, and we deal with the special case of an icy catenary. Let's continue. Which are the reason of arcing phenomena? Track irregularities, irregularities of catenary, high speed, weather conditions, which are the consequence of a huge number of arc events, fast degradation of the collector strip, increase of arc events, decrease of power quality. This is very important because in some cases, the arc events trigger the main circuit breaker or produce problem to converters on board train and even accidents. Here you can see the experiment we have performed in RIM laboratory. The aim is to acquire the voltage rising across an arc between two contacts. We emulate the catenary with this big hole, and we have a pantograph, a contact strip, which is fixed. So in this way, we emulate the arc events. The setup does not reproduce the real mechanical condition experienced in railway sliding contact, but it's a good arc generator. Here on the right side, you can see a collection of voltage and current samples, the time behavior of voltage and current. And you can see that the magnitude of the arc voltage, that is typical 20 volt, it increases if you have an extension of the arc. Which is the first conclusion? As first approximation, the arc can be introduced in a circuital model as an impulse voltage generator. You can see, for example, in this case, that this is a pulse voltage. So we can emulate in a simple way the arc by introducing this behavior. We also fix the time duration of such arcs, milliseconds. Now I jump on I'll present the measurement campaigns, but even in next presentation, the setup used for the onboard measurement will be described. We arrange the measurement setup on board E46441 operating in Piedmont. We collected a lot of data, which are the quantities we measured. We sampled at 50 kilohertz, the voltage and the current at pantograph, the voltage downstream the filter. Here you can see the structure of the input stage of the locomotive. We have the braking chopper and the rheostat chopper. We also monitored the chopped current flowing in the rheostat. Okay, now here you can see the voltage and pantograph detected during the journey Novara-Domodossola. There is an arc event. There are arc events in this data. We can see strange behavior on the pantograph voltage, but we have also false friend, which is the arc. Here you can see the arc. Let's enlarge this picture and let's have a look in the zoom what occurs. You can see the voltage, what's happened to the voltage at pantograph and the current at pantograph. You can see this oscillation. So we will analyze this effect. Before introducing the analysis, we have performed probably this sketch electrotechnical circuit allow us to understand what's happened when an arc occurs. You have the detachment between the pantograph and the overhead contact line. As I show you before, the arc can be simulated by voltage, the arc. And you can see the second order filter placed in the input stage of each locomotive. VP is the voltage at pantograph, V line is the voltage before the arc, and VF the voltage after the filter. In the case of the traction, the current EP is positive, is absorbed by the locomotive, and you can see that the voltage V arc is not a generator but absorb energy. In fact, in reality, the arc absorb energy. What's happening in the braking? For what concerns the voltage, nothing is similar as in traction, but the current now is generated by the locomotive. So it means, considering that the arc has to absorb energy, you can see that the positive sign of the voltage generator is moved on the inductance side. We also developed a circuit model in order to understand, to investigate on the conducted phenomenon produced by the arc. Here you can see a simple circuital model. As you can see, the only generator of this circuit is the voltage arc, the voltage arc. We removed the DC source, and we analyze the circuit considering as a source only the voltage at the arc, produced by the arc. And on the right side, you can see a comparison between measurement and computation by considering the voltage arc profile you can see on the left side. Here you have an example of an arc event. On the left side, you can see the three quantities: the voltage Vp at the pantograph, the voltage downstream the filter of the locomotive, and the current absorbed by the locomotive. You can see that we have a voltage of 3.6 kV and an absorbed current of about 400 amps. An arc occurs. So as I told you before, the arc produces a voltage dip at the pantograph. The voltage downstream the filter has a delay, so we have a voltage across the inductance that manages the current. The current decreases. The current reaches zero, so the arc is switched off, is in quenching, and in this case, the locomotive is isolated by the supply system. In fact, you can see that the voltage at the pantograph becomes exactly equal to the voltage downstream the filter, because you have not voltage drop across the inductance. After that, again, you have a good contact between pantograph and contact line. The voltage at pantograph rise immediately at the previous value, about 3.6 volt, and this produces an oscillation due to the second order filter. You can see this big oscillation, and let me say nice oscillation, as you can see when you study second order circuit. But it's a big oscillation. It reaches 1 kiloamp. What's happened when we are in the breaking stage? As I told you before, we saw a voltage dip. Now we saw a voltage, an increase of the voltage at pantograph. Even in this case, we have the arc quenching. So the current reduces when it passes through zero. The locomotive is insulated by the supply system. But what's happened, as you can see, the red signal, the voltage downstream filter increases. And as will be explained later, this produces the effect produced by this increase is related to the rheostat, braking rheostat. The locomotive thinks that the receptivity of the line is reduced. So during the regenerative braking, the energy will be sent to the rheostat and lost because of the filter. Here you can see a collection of arc events we have published in a data set. We collect data in railway application and metro application for traction and in the braking stages. And let's have a look to statistics. As I told you, the locomotive, the first locomotive we have equipped with our system, running around Piedmont lines. And here you can see the number of events we have detected for different journeys. Red is the arc event during braking, and black the arc event during traction. This is to highlight that the detection system is very useful if you want to perform maintenance, and we want to see how many events occurs during a line, in which position, and so on. Here we have another example, another locomotive, A4C4354, running between Roma Termini and Foligno. During this journey, there is a section in which the trains reaches the maximum speed of 160 km per hour along a section of the high-speed Roma-Firenze. And for example, here we detected 4 arcs only on the high-speed section and no arcs in the other part of the line. This could be very interesting for, as I said before, predictive maintenance. And let's have a look to the statistic data related to Metro de Madrid. We monitored the line 10B of Metro de Madrid. And you can see that we detected more than 150 events over 21 hours of analysis. I have to say that line 10B is equipped by rigid catenary. Maybe there is a relation between number and the fact that we have a rigid catenaries. Of course, this is not the aim of the project and of this presentation to provide satisfactory statistics and analysis, but just to highlight the advantages of the methodologies. We have submitted a patent on the methodologies to detect the arc event. The methodologies can be implemented in the energy measurement function by providing a new functionalities for the energy measurement function that could allow the predictive maintenance related to the quality of the contact between pantograph and overhead contact line. And now, the strange case of an icy catenary. The data was collected along Alessandria Novara route. The train was the first one of a frozen morning. You can see here that we have a noisy signal on the left and a cleaner signal on the right. What's happened? Let's go inside. As you can see, the contact is very bad between the pantograph and overhead contact line. When you have a good contact, the current starts to oscillate at the resonance frequency of the filter, which is about 50 Hertz. But when the current passes from 0, you have the quenching of the arc. You have to wait again a new good contact, the current start again to oscillate, and so on. So you have a very bad contact. This is the case we investigated. We have a single track line. We are in a station. Okay, the train monitoring is coming from the IC catenary. It goes, it takes the switch and goes on the other track. You can see here the behavior of the voltage at pantograph. Very noisy. At a certain time, because of power quality problems, we have the circuit breaker that open the circuit. It was closed again, the main circuit breaker of the locomotive. The train starts, and you can see that is cleaner, the catenary. Why is cleaner? Because another train comes in the opposite direction and cleans the catenaries. All these things can be seen by analyzing the data at pantograph. The same thing can be seen observing the 50 Hertz component. On the left side, you have a high 50 Hertz component because of the oscillation of the filter. On the right side, with a cleaner catenary, we have a less magnitude of the 50 Hertz. Very interesting. And now the last case is related to energy. contained by inside absorbed by the arc. As you can see, if we analyze the single arc, the energy, the arc is a phenomenon characterized by high power but low energy because the duration is very low, tens of milliseconds. So you can see that the energy absorbed is very low. But we have a very strange phenomenon due to the high voltage level that is typically high at the pantograph. What's happened when an arc event occurs during a breaking stage, like in this case, the voltage, the red signal, that is the voltage downstream the filter increases, and this switch on the braking rheostat. Because for the locomotive, it is like to see a reduction of the receptivity of the line. Because of the duty side, because of, sorry, the hysteresis of the control system that control the braking rheostat, we can stay in this situation for a long time. So we can see an extra energy dissipated of 3 kWh due to an indirect effect of the arc. So this is a consequence of the arc. Thank you for your attention. I think we can move on the next presentation and then in the debate to collect question. So I give the floor to Daniele Gallo from University della Campania that will present an overview of the power quality in DC railway and metro system. Thank you.
Good morning to everyone. I don't see the presentation.
Just a moment, Daniele, they have to upload the presentation.
I'll be fast because we are a little late. Anyway, I'll try to give you an overview on how it's possible to use the data coming from monitoring of power quality to obtain important information that could be used for predictive maintenance or to early detection of problems that could be arise on DC supply network. The presentation is not yet arrived. It's impossible to talk about all the power quality phenomena, so I just focus on some of them. We can, okay, this is okay. Okay. I simply want to just add to what I have already said, that for a railway system, we are obliged to have a double point of view. Monitoring of power quality should be performed both in substation and onboard train, because we can see different phenomena, or we can see the same phenomena but different point of view, gathering so different information. This is a classification of phenomena. I don't want to go in deep of that. Let's start with the first information about the quality of supply. It's of preeminent importance, the stability of voltage. This is for an example of a statistic of voltage monitoring inside a substation. This is for this substation. You can see that the voltage is quite higher than nominal value, but is a very stable value with very little variations. obviously, the point of view of a train is quite different due to the voltage drop along the supply line. This is, for instance, the route Alessandria-Savona. You can see large voltage variation with very low value, till reaching the value so also below 2600 volt. That is that are very low value for a 3 kV nominal value. This is probably an overloaded line that need maybe maintenance or some improvement, because this is not always the situation, because we can see this is another route, Novara-Domodossola, and the voltage reduction is much lower. This kind of monitoring of voltage can be used for maintenance of different line, and to keep under control the different state during the time of the considered line. This is an example of a voltage interruption. You can see that we consider a train that is braking, high negative current, but during the braking, the voltage, the blue line, had a sudden drop, probably some problem in a substation, and the problem keep on be present, and the voltage keep on reduce. So the main circuit breaker opened, and the train was disconnected. This is for some seconds, some tenths of second. Then the circuit is again closed, and here you can see what happened at the reclosure. We reach an amount of 6,000 of volt. So a big value, even if this value is experienced by the device for very short time. These are data collected at 50 kilohertz. So we can see also very fast phenomena. This is a similar event that I jump. Ripple. In DC, one of the main problem that can be found different from a system is the fluctuation around the average value due to the working of rectifier and older time-varying devices. This is an example of two recorded ripple. On the left, you can see the ripple in Metro Madrid DC railway system, and on the right you can see a ripple, an example of the ripple in the Italian railway. The value are almost similar, even if the shape of ripple in Italy seems more regular, seem almost sinusoidal. Anyway, if you focus on the average value of the different system, we realize that we have a very different situation, because here we have a 1.5 kV system. So the oscillation in this case is 5% of the main value, and in the other situation we have only 2% of oscillation. The reason of this difference in the system, in the metro, they adopted a rectifier without any filter. So And while in Italy, the rectifier is followed by a second order filter. So you can appreciate from this slide the effect of a filtering on the voltage stability. We can analyze the ripple in more details. For instance, following the change in ripple amplitude during the time, during the working. This is the ripple during a work day recorded on board in a train during its normal working. You can see that the value changed during the time, reaching sometimes also higher value. The ripple can be analyzed in terms of spectral component. The main component here are 600 and 1200. This is obvious because we deal with a 12 pulse rectifier, but in this case, it's interesting to look also other components, even with the lower amplitude. In fact, in this case, the 300 component and the 2400 component have a strange behavior. It seems the amplitude keep on go low and high in a repetitive way. The both apply for the same apply for both components. So it seems that there is a time periodicity of this kind of pollution. It's not a big pollution, but it's interesting to understand the reason of this periodicity. We focus on one of them, and the periodicity was about 51 minutes, and finally we analyzed the current during this time interval, and this is exactly the path that the trains, this is exactly the time that the trains takes to go from Tres Olivos to Hospital Santa Sofia and then back again to Tres Olivos. So the disturbance has not a time periodicity. This is a spatial periodicity. The distortion came from Tres Olivos station. This is a connection station that connects many lines. So probably a different line inject this kind of disturbance in line 10B that was monitored. So what seems time periodicity on board train from the point of view of the station is a spatial periodicity. We have found the source of this disturbance. This is a strange ripple event. Normal ripple amplitude in Forlì substation is quite low, as you can see from the red line, but during a specific day, we found a huge amount, 300 volt, that also caused the disconnection of the station. Here you can see where the station is disconnected due to the too high pollution level. Analyzing this ripple, we found that it was composed by a 100 Hertz. This is a very strange because it's not an expected frequency for the considered system. Finally, we discovered that the Imola station had a problem with the medium voltage circuit breaker. After a reclosure, only one phase remained connected. So the system worked as a single phase rectifier. This justified the huge amount of ripple and also the frequency of the ripple. The anomaly was detected by RFI personnel and resolved in few hours. Just a look to transient events. Here you can see the voltage during a route in Italy, a normal route. You can see a lot of spike of voltage. This is a very fast phenomena, a few milliseconds, but the range of the involved voltage is about of 1 kV. Analyzing these phenomena, we found that they are caused by a step change in current. Each time the current has a step change, the voltage has a transient event of this kind. And the reason of this so frequent event are in the current of auxiliary services. In red, you see the step change of auxiliary services current, and in correspondence of each step, you can see that there is a transient event of this kind. Probably a smooth insertion of these loads could solve this kind, could avoid this kind of event. I will show you also a bigger step change. Here we have a train that is in traction over 1,000 of amps, and something went wrong, and the main circuit breaker opened, and the current suddenly go down. This trigger high oscillation in the voltage of the system. You can see that this lasts a longer time with a big oscillation. This is another transient event. Here we reach 6,000 of volt. Anyway, a huge number of different power quality events occur in DC power supply system. In most of cases, they do not cause any trouble because the great immunity of devices devoted to railway application. Anyway, it's important to monitor this event for the negative effects that they can cause in some particular situation. Constant monitoring can give precious information for system manager for predictive maintenance and early detection of a malfunction. We have a big problem in performing this kind of monitoring because of the lack of standards explicitly dedicated to DC power quality. So there is a certain arbitrary in event classification and in measurement technique. And I think that there is the needing of more work on this field. To this aim, we are also starting a new research project on standardization of measurement for the sea electricity grids, coordinated by Helco van der Born from VSL, in which we try to tackle this problem. That's all for my presentation. I thank you for
Thank you. Thank you, Daniele. Thank you very much for this nice overview on power quality events. I think it's quite new, the analysis of power quality in DC railway systems. I have to highlight this aspect that, for example, the voltage level, that is a power quality parameter, can affect the efficiency of the whole system. So here we can, I want to highlight the relation between power quality and the impact on the energy efficiency that will be discussed in the afternoon session. And moreover, I think it's also interesting, especially for what concerns the transient events, to know, to see these events that can, for example, degrade the insulation. Because if you have such fast transient event in terms of voltage, you can degrade the insulation, and so is an important power quality event to be monitored for predictive maintenance, such as, for example, arc events. Okay, we are not in time, so I suggest to skip the time to debate and to have the lunch break. Maybe if you have some question regarding the sea power quality, you can also write in the chat the question. So I can say see you after lunch, if you agree.
Okay.
Okay, Domenico.
Okay.
So we start in time after lunch.
We will. Yes, yes. I suggest to start at 2, or it's 2. We have no time. What do you suggest? It's better to start at 2 or
2 is fine.
Okay,
it's fine.
It's better.
Okay, okay. See you.
See you. Ciao.
Good afternoon, everyone. We start the last session of the workshop Metrology and Measurements for an Efficient Electric Railway System. The session deals with the energy saving. The title is Where We Found the Energy to Save, the Braking Energy and the Eco-Driving. The first speech is presented by Paloma Cucala Garcia, Universidad Pontificia Comillas, Spain, and the title is Energy Saved by Eco-Driving in the Metro de Madrid and Bologna-Rimini Railway Line, Test Cases. So please, Paloma, you have to unmute. Okay, thank you.
Thank you very much,
And
Domenico.
we will wait for the presentation that has to be uploaded.
Okay, fine. It's a pleasure to be here presenting this piece of research that is focused on eco-driving in the framework of the MyRailS project. You can see there the title of the presentation. I work at Comillas University in Spain, and we've been working for quite a lot of years focused on energy efficiency in railways. So I will take the control.
Yes, you have to take the control. On the top, there is a menu, view options, request for control.
Okay.
Okay, good.
So this is the methodology we've applied for the work package related to eco-driving in MyRailS project. We have a typical driving that will be the reference we want to compare with the new way of driving that we will design, that is the eco-driving style of driving. This eco-driving is a style of driving that makes use of cost commands in order to reduce and minimize the energy consumption. We have to make this design by means of the use of a simulation model. Why? Because it's very difficult just to find the best solution, just trying by means of a trial and error with real trains. Instead of that, we need an accurate simulation model that once has been tuned, we can use it in order to optimize the way of driving. So we tune the simulation, comparing it with measurements, real measurements on board the train. And then once we are confident enough on the simulation model, then we use it to optimize the driving, to obtain the design of the eco-driving. Then this eco-driving, apart from being simulated, of course, it is tested in real trains and measured. And we compare both results, simulations versus measurements, and as well reference measured driving with eco-driving measured. And this way we can calculate the energy savings we have obtained. This methodology has been applied to these two test cases in Metro de Madrid in Spain and in Italy Railroad Network in Rimini-Bologna line. The simulation model has different modules that have to be model, programmed model, and tuned by means of measurements. One of them is focused on the way of driving. It could be a model for the manual driving, or in the case of Metro Madrid, it has to model the equipment on board the train that is corresponding to the ATO system, that is the automatic driving equipment for the train, because these trains in Metro Madrid are driven automatically. We have another module, simulation module for the motor of the ratio, efficiency ratio. Another module for the dynamics consumption, the model of the train data, track data, aerodynamics, and so on. Then, by means of measurements on board the train, we tune the simulation model And then once the result is accurate enough, then we use it simulating lots of possible drivings in order to optimize and obtain the best driving, minimizing the energy consumption. If we represent in this graph, each dot would be a way of driving in a specific stretch and a specific interstation. If we represent the x-axis, the running time, in the y-axis, the energy consumption, this set of dot we have here different drivings, we have to select those that are in the Pareto curve. That means those that are optimal in the sense of energy consumption. So we design the eco-driving, we obtain one of these speed profiles, and then we apply them in the real line in order to take measurements. Now in the following, I will show you the tests performed in Metro de Madrid. In Metro Madrid, 4 interstations were selected in line 10B from Marqués de Valdavia up to Hospital Infanta Sofia, that is this one. So this Hospital Infanta Sofia is the terminal station. The line has been modeled, the rolling stock has been modeled, the ATO equipment has been modeled, that is the equipment of Siemens with its specific algorithm for the control, specific parameters and values that can be given to these parameters. And the eco-driving was designed simulating first a typical journey, the reference one, and then the ATO parameters of this Siemens equipment were optimized by means of the simulation model. Then the simulation, the eco-driving design was simulated again, and these were the ATO parameters that are optimal to obtain an eco-driving. Given a specific deceleration, braking deceleration, the coasting speed, and the remotoring speed that will be programmed on board the train. If we compare simulation with simulation, the reference driving with the eco-driving simulated, we obtain these energy savings we would expect when we later will try on the real line. So we are expecting, according to our simulation model, that in the first interstation we could obtain a 15% of energy savings. The second one is quite high, more than 50% of energy savings, considering that the time difference is just 7 seconds. And similarly for the other 2 interstations. Then a measurement campaign was executed by Metro de Madrid in these 4 interstations, and measurements were recorded for the reference driving. In here, you can see the comparison between the simulated speed profile in blue and the yellow one that would be the measured speed profile we obtained with this night test. This was performed during the night test. And it's quite similar, it's quite accurate. Here you can see as well the comparison between the simulated traction effort and the measured traction effort. That it's quite similar in here, not the same, but quite similar. This would be the second interstation. At this point, it starts braking a bit slowly and then a faster braking effort. And this is the third interstation and the comparison between the simulation and the measurements. And finally, from Reyes Católicos up to Infanta Sofia. This time, there is a difference in here, quite clear, and this was due to that it was scheduled that driving from Reyes Católicos up to Infanta Sofia, that is a terminal station, should go through the same track 1 up to platform 1. But that night it changed, taken the point and changed from track 1 to track 2, and that is why this speed was reduced. So it was not executed exactly as expected. Then here we have the comparison for the reference driving style between the simulation and measurements. And it can be seen that they are quite similar. The differences are small. And here we have the measurement campaign corresponding to the eco-driving. Once the parameters of the ATO that have been optimized are programmed on board the train, they were executed in these 4 interstations and measurements were recorded. These measurements were made using the already existing measurement device, because the other one, the energy measurement device, was not available at this moment. You can see the comparison between the simulated speed profile and the measured speed profile, that they are nearly the same. At this point, traction effort goes to 0 because this is the coast command that has been programmed on board the train, on the equipment. And as it is an automatic system, as it is a program, a software running on board the train, it is executed exactly, and traction effort goes to 0.0. So in this part of the speed profile, the energy consumption of the motors is null. Here we have the second interstation. This interstation cuts traction effort at this point. So nearly just a few meters after departure, the coast is applied. That is the parameter that was optimized and programmed on board the train. And even with null traction effort, due to the slope of the track that goes downhill, the speed of the train increases. And then at this point, the train starts the braking because it's close enough to the station and it has to start the braking process. And here we have the eco-driving of the third speed profile, similarly, and the last one. And in this table, you can see the comparison between the simulation and measurements of the eco-driving style. And differences are small. And here we have the information about energy savings obtained. Here we have what we measured, comparing the measured speed profile with the measured eco-driving. And these are the energy savings that were obtained at each interstation: 15, 52, 43, and 39%. And then the comparison between what we expected related to energy savings using the simulation model and what we have measured on the line with real measurements. And we can see that these errors, the expected energy savings, were very close to those we obtained in the line. Now, I will show you some of the results we have obtained for the Bologna-Rimini line. In this case, we are still working with new measurements, so these are partial results of the tests that have been executed on the line. We have information about the reference driving measurements in the 1st of January of this year, and the eco-driving that was executed on December of 2020. And these were the interstations. These 4 interstations were measured that you can see here from Rimini up to Bologna with 3 intermediate stops. However, we had in one of the cases, we had some missing data in the second and in the third interstation. So in order to perform a fair comparison between reference and eco-driving, we have focused the analysis on the first interstation and the fourth one. Okay, these are the two types, these are the two types of measurements we have from the line, from RFI and Trenitalia. We have information data from the telediagnostic system. And in this case, we have data for the speed of the train, the traction effort. And in one of the cases for the eco-driving test, we have as well the current at pantograph and the voltage at pantograph. And the time sample is 1 second. And we have data from the energy measurement device. We have electrical measurements, the current at pantograph, at auxiliary systems, rheostats, voltage at the filter, voltage at pantograph. Samples, depending on the test case, we have samples every 100 milliseconds or every 10 milliseconds. And given this information, at each time step, we calculate the current of the motor in order to calculate the power of the motor and the energy consumption. You can see here the stretch from Rimini to Cesena, the reference driving, and in here, the 17th of December, the eco driving. And both are shown the simulated speed profile and the measured speed profile. And as well, the other graph in yellow and orange, they are displayed the traction effort, the corresponding traction effort, the simulated and the measured one. The accuracy is not as good as the test case in Metro, mainly because of the manual driving. In here, we simulated that the speed increases up to this maximum speed limit, but the driver started a braking process and then a traction again. So that is why there will be always more uncertainty associated to this way of driving, the manual driving, than the one that will be executed by the software. Similarly, we can see in the eco driving one that the simulator cuts traction effort at this point, but the driver still applies traction effort a bit more and then brakes and then, yes, cuts the traction effort. So it's approximated. The command that is caused at this point is approximated by the driver. And this is the other interstation from Castel San Pietro to Bologna, the reference driving and the eco driving. And well, you can see, for example, in the eco driving that the command was to coast at this kilometric point, and it is executed quite similarly. Indeed, if we could make zoom here in this part, we would see that in the simulation, the traction effort is completely null, but the execution of this coast command has a ripple when it's executed by the driver, and it's not exactly zero. That will make that we have been measuring as well during the coast period, we have been measuring as well some consumption, energy consumption. Here we have the comparison, the energy savings between the simulation and measurements, and we compare, here we see the table measurements, the reference energy consumption with the eco-driving energy consumption. The energy savings that were measured on the line were in the first 16% and in the second one 8%. This second one is quite different to the expected one by the simulation tool. The two main differences can be given due to the fact that the execution is the driving is not automatic, it's performed manually, and thus it won't be executed exactly at the point that it is supposed to, and that the approximated execution of the coast command makes that energy consumption has been measured also during the coast period. Anyway, it has been demonstrated that very important energy savings can be obtained by the application of eco-driving. It will be very systematic if it is programmed on an ATO equipment, because it will be automatic, that it can be very, very useful and very efficient also when it is executed manually by a driver. So that's it. If you have any question now or later, thank you.
Thank you very much, Paloma, for this nice presentation that also highlights the impact of the eco-driving. I think that Donato would like to comment to this presentation.
Sì, innanzitutto ringrazio la dottoressa
Yes,
Cucala.
absolutely. Thank you, Dr. Cucala. It was a brilliant presentation. You have basically explained to us automatic driving. I just wanted to highlight a focal point for the EU, which is automatic train operation. And I wanted to highlight that there have been several experiments with an Alstom train in France with automatic driving, and these have been also executed by Siemens in Germany. Automatic driving system need a signaling support, and given that the European Union has decided on a specific system, I wanted to relay important words. In the Next Generation EU funds, we need to invest in RTS and on onboard system. These will be given to each member state in the form of 750 million euros to invest in this system. So I believe that we have been given the means and the tools to operate to contain energy consumption.
There is a draft of the standard ERTMS that is focused on the ATO over ERTMS. It is not, it has not been approved, but several companies are developing their own ATO over ERTMS, and as well in Spain. Not using this standard ERTMS, but Renfe bought several high-speed trains in Spain to Talgo, and it will implement an ATO that will be executed on the high-speed line.
Grazie. Thank you.
Thank you.
So now I have to give the floor to me again. I will present. Sorry, maybe the.
Look at te.
There is a problem with the mic.
Okay. Now it should work. Okay. Okay. If we have no other questions on the Paloma.
Sorry, I have another question.
Yes.
Can you hear me?
Yes, yes, very well.
Okay. Good afternoon, everybody. I have two questions about this last presentation. The first question is, the two questions are for Paloma. The first question is, according to you, which is the main features of the speed profile that can affect the energy savings? And the second one is about your simulation in Metro Madrid. We have seen that between the different interstations, we have a different energy saving ratio with respect to the traditional driving. And so this second question is, according to you, which is the features of the line, of the route that can affect this energy saving ratio? Thanks.
Just a moment. Can you introduce yourself?
Okay, I am Alessandro Borselli. I work for Trenord, Italy.
Thank you. Thank you very much.
Okay, one of the parameters that affect a lot the difference in the energy savings that can be obtained and that can be seen in the different interstations in Metro de Madrid is the slope of the track. Of course, if it's downhill, the slope of the track, it will be possible to even increase the speed, so run faster without applying traction effort. It means that we can save a lot of energy. On the other hand, if we have a steep uphill ramp, it will be highly energy consuming, and it will be more difficult to save energy. On the other hand, typically, what we gain when we go in one direction, if it goes downhill, then in the other interstation, in the other sense, it will be uphill. So it will be compensated. It won't be always bad or always good. But it will be very important, the different slopes we will have along the track. And it will be very important to take it into account in order to locate the coast at the precise location according to those slopes. I will never coast if I have different ramps and slopes. I will not locate the coast at the ramp, that better at the beginning of the slope. And the other question would be, what other parameters could affect? It could affect as well if the schedule of the line is very, very tight, because the train has to run as fast as possible. It won't be possible to use these time margins in order to save energy. If the timetable is so tight that it is necessary to go as fast as possible, it will be never possible to apply cost and to lose time saving energy. It will never happen, because a commercial timetable is never exactly the minimum running time possible, because it will be always delayed. But depending on the time margin we have in the timetable, we can have more energy savings or less energy savings.
Thank you. Thank you, Paloma. Other question?
Thank you.
Okay, I think we can move on next presentation. Accurate measurement of power dissipated by braking rheostat. It's another source of energy we can save. Okay, I take the control. Okay, so a few words about braking rheostat. As you know, in railway system, the braking is commonly regenerative. So the motors for traction becomes generators, and the energies can be recovered if there are other trains, other loads that can absorb such energy. Otherwise, the voltage of the system increases, And the control system on board train connect in parallel with the motors resistor, which is variable thanks to the chopper, in order to waste this energy. You can see in the slide a simplified circuit that explain how the current, so the power generated during the braking, can be divided between the overhead contact line, and so the railway system, and the braking rheostat. Braking rheostat are generally placed on board train, and as I told you before, the aim is to transform electrical energy to dissipate such electrical energy. Let's have a look to the two methodologies actually used to estimate such energy. As you can see, we have two possibilities. The first one is starting from the knowledge about the braking effort, the speed, and the efficiency of the electric motor. With these two information, we can estimate the generated energy, electrical energy during braking. We subtract the power sent back to the catenary, and so we obtain the power dissipated by the rheostat. Another possibility is to detect the peak of the chopped current, and with information provided by the control, the metro control, the locomotive control system, the duty cycle imposed to the chopper, we can evaluate an average value of the current, the square of this current multiplied by the resistance, provide the power dissipated by the rheostats. These approaches are affected by high uncertainty. For example, in the first case, if you think about the efficiency, the knowledge of the efficiency of the motor is has a higher uncertainty. You do not know exactly the efficiency of the motor in the different operating conditions. And for what concerns the second stage, the second case, for example, the resistance can vary. We are not measuring the duty cycle. We just take the information from the control unit. The approach proposed by MyRailS requires the acquisition of the chopped current and the voltage of the locomotive at DC link with a high sample rate. You can see on the left side the scheme of the structure of the locomotive E464. We have two inverter series connected, and so we have two resistor element, braking resistor element, and two choppers. On the right side, you can see the magnitude of the chopped current. So it's quite challenging to measure accurately the current because, for example, you can see that the current jumps from 0 to 1,200 amps in a few tenths of microsecond. So it's quite challenging to perform such measurement. Nevertheless, we try to perform this measurement. You can see here a small model that allow us to correct the measurement we have performed on board train. You can see the model of the rheostat in which we introduce the inductance, the strain inductance associated with the resistance of the rheostat. And the GTO or IGBT, depends on the technology we can find on board train, is simply emulated with a pulsed voltage generator. On the right side, you can see what's happened. This is the case of a train from Hitachi Rail running on line 10B of Metro de Madrid. When you have a very low duty cycle of 0.7%, you can see here in red the pulsed voltage applied. and the current, which is smooth because of the strain inductance. And you can also see, comparing this picture with the picture in which the duty cycle is 15%, that the current has not the time to reach the peak value because it's very short, let me say, T-on. The proposed measurement model introduces a systematic error that is estimated and corrected. You can see here on the left the correct estimation, and the area, the green area is related in some way to the energy, the power dissipated to the braking rheostat, and so the energy. The actual, the right area. On the right side, you can see the wrong estimation we are performing. You have to consider that we are measuring just the DC voltage. We have not information regarding the pulsed voltage, but only pulsed current. So if we multiply, as is presented in the slide, we multiply the voltage, the DC voltage, and the current chopped, the chopped current, we perform an overestimation of the area, of the green area. Thanks to the numerical model, a correction factor as function of the chopper duty cycle can be computed. Let me spend a few words about the challenging regarding the accurate characterization of current sensor. Here you can see a methodology to evaluate the accuracy of sensors when a pulsed current has to be measured. So this setup allows to compare, allows to generate a pulsed current thanks to a variable load, and to compare information provided by the device, the reference transducer, which has a large bandwidth, with, for example, commercial transducer characterized by lower bandwidth. And you can see the comparison on the right side. The second approach, so the first approach is, let me say, in the time domain characterization. The second approach is a characterization in the frequency domain. It means that we can apply a sinusoidal distorted current, for example, with the fundamental component DC, for example, plus harmonic at variable frequency. We can perform a sweep frequency in a specific bandwidth, and we can obtain, as you can see on the right side, the frequency behavior of the gain of the sensors. Thanks to this information, we can try to fit the gain behavior in order to extrapolate an analytical function that we need to perform the correction. You can see an example on the left, an open-able sample, which has the rated bandwidth minus 1 dB at, sorry, there is a mistake, not 1 kilohertz, but 10 kilohertz. Okay, so we have the model to estimate the real behavior of the current flowing in the rheostat, and we have also the model to estimate the distortion introduced by the sensor, which has a limited bandwidth. You can see here a comparison with two different duty cycles of all these quantities. We have the sampled emulated current. It means that we emulate current in the time domain, and we try to sample considering that in reality on board train we are sampling the waveform at 50 kilohertz. So it means that for this current pulse, which is a real current pulse, we have a few sample point. that we use to estimate the dissipated power. We have also the current IOP, that is the current emulated, that emulate the signal provided by sensor. In blue, the current that we actually, sorry, in red, the current that we actually measure. So the real samples we capture on board the locomotive, the train, and in blue, the simulated waveform. So you can see here the difference between simulation, that let me say is the actual current behavior, and what we are able to do by sampling. Of course, with an increase of the duty cycle, things are better in the sense that we have many samples that allows us to reconstruct the time behavior of the pulse. And on the right side, you can see what's happened because of the phase displacement, that is stochastic information, the phase displacement between our sample phase, the phase of our sampling, and the phase of the pulsed current. You can see here different situation, and these affect the behavior of the current, and so the area we have to estimate to quantify the dissipated power. Here, the procedure we propose. As I told you, we have two correction factors. One is due to the model of the measurement, the other due to the distortion introduced by the sensor. Okay, so on the left side, you can see the quantification of the two correction factors and the procedure in the flow chart. We measure the current, we evaluate the duty cycle of the current, we estimate through the model the duty cycle of the voltage, which is different, especially at low duty cycle value. And we estimate, thanks to this duty cycle, we will estimate the correction factors. With the current duty cycle, we can evaluate the, let me say, wrong power, and by applying the correction factor, we extrapolate the right power. Here, an example of the application. You can see a braking detected in line 10B of Metro de Madrid. You can see that the braking duration is about 11 seconds. The mean voltage is quite high. You have to consider that the rated voltage for such line is 1,500 volt. We experienced the 1,780 volt. The average power is about 40 kilowatt, and the average duty cycle is 6%. You can see in the graph the behavior of the duty cycle. We goes from about 16% at the beginning of the braking, and we have the lower value that is about 4%. Here you can see, let me say, this is the conclusion of this presentation. You can see here the input, the impact of the corrections factor for different value of duty cycles. You can see the power estimated at first attempt and the corrected power, the quantification of the deviation between the two powers, and the variability due to the unknown phase between our sampling and the pulse current. You can see in the bottom of the slide two applications. For railway application, for example, in Rimini-Bologna journey, we have an average duty cycle of 30% with a standard deviation of 50% of such duty cycle. But we have to say that the impact of the corrections is lower in railway application because of the lower switch frequency. We have a 300 Hertz as a switching frequency for E4C4 locomotive, And for Metro de Madrid, we have 1 kilohertz as a switching frequency. You can see here the statistics on one day with high traffic density and low traffic density. And you can see that generally the duty cycle is quite low in both cases, 2.8% with high traffic, 3.6% with low traffic. And the maximum duty cycle is also, let me say, quite low. It means that the duty cycle is not, the braking rheostat is not so used, but probably it has been designed for conditions that are not the real conditions experienced in the line. Of course, just to conclude, I want to highlight that the aim of this activity is not to perform a complete analysis of the duty cycle, but just to provide tools to perform such analysis. I conclude with this last slide. If you have any question. Okay. It seems that there are no questions, so we can move on next presentation. Antonio Delle Femine from Università della Campania Luigi Vanvitelli.
Good afternoon.
Yes, please. Just a moment.
I don't see my presentation.
Just a moment. Here it is.
Here it is.
You have to take the the control.
Okay. Okay. Good afternoon. Really pleasure to be here. I'm Antonio Delle Femine from University of Campania. And I will speak about braking energy. As mentioned by colleague, we make 3 measurement campaign on board the trains during this project, 2 on Trenitalia rolling stock and 1 on the subway line of Metro de Madrid. I will use this little flag to indicate whether the results come from Italian or Spanish campaign. For sake of brevity, I report a single block scheme of for the 2 trains. Of course, the 2 trains are different, but from measurement point of view, they are quite similar. We monitor the quantities with the same meaning on both locomotives. For both, we have acquired current at the pantograph, voltage before and after the filter, currents coming from the braking chopper. The braking chopper is the device that regulates the share of energy dissipated on board. For design, we have developed a proper measurement system with the opportune voltage and current transducer. Note that the traceability has been granted because all transducer has been calibrated at INRIM, and we have recorded more than 6 terabytes of data across the 3 campaigns on board the trains at 15 kilohertz of sampling rate. As mentioned by Domenico before, the dynamic braking has the capability of convert the kinetic energy back to the electric form. The dynamic braking allows injecting energy back to the catenary when possible, and it is not always possible. It depends on the line receptivity that on turns depends on the possibility of having another train interaction on the same section of line in that moment. Otherwise, the chopper wastes energy on the rheostats. So greater number of trains means greater probability to recovery. Possible strategies to overcome this problem, this limitation, is the adoption of reversible substation or storage systems. Let's take a look to the measurement. In particular, here is some data acquired during the Freeze Rail campaign in the northern part of Italy. This is the traction current during a journey from Bardonecchia to Torino. It is possible to distinguish the traction positive current from the negative current. Note that there is a considerable amount of current regenerated during braking on this track, 800, 900 ampere, because of the path is downhill, and for this reason there is a strong need to brake. This is possible because, of course, there is another train going uphill. Instead, this is an example of traction current acquired on the S9000 metro train during an entire journey on the line 10B. It is possible to distinguish the 11 stops that correspond to 11 acceleration exiting by the station and deceleration approaching to the station. Focus now on a braking event. This has been acquired in Madrid, but similar behavior has been measured also in the rail case. The quantity depicted are those seen before, the pantograph current and the voltage after filter. We can see that approximately around second 20, a brake start. A strong brake starts with complete recovery. In fact, if we add also the rheostat currents, we can see that it is almost zero until the second 35, where rheostatic braking starts, and this happens exactly when the filter voltage overcomes the threshold limit of 1,700 volts. As you can see from this zoom, in this condition, not all possible energy regenerated is reinjected on the line, but a certain amount of this energy is dissipated on the rheostat. This last signal is the average value of the rheostat's current, and as you can see, it is not constant. In fact, as mentioned before from Domenico, the average value depends on the duty cycle of the chopper, that is a PWM modulated signal, and it vary during the braking depending on the line receptivity. This is the statistical analysis of the duty cycle. As mentioned before by Domenico, the line receptivity changes significantly with the number of trains. In particular, using the timetable of Metro de Madrid, it has been possible to separate data related to higher passenger transit from that with the less transit. And we performed a statistical analysis of the chopper duty cycle in the different moment, and it is evident that the duty cycle maintains at low level for most of the time, even when the line receptivity is low. And this could suggest that that the rheostat may be somehow oversized. sorry. Here we have the picture of two braking, the most regenerative braking on the left and the most dissipative one on the right. And under the figure, we have the four most regenerative braking on the left and the four most dissipative braking on the right. Note that all the four regenerative happen during a high transit period. Meanwhile, all the four most dissipative braking happen with less number of trains in service on the line. The resistance of the rheostat is expected to vary during a break. And let's come back in Italy to see this variation of resistance, because in general, we can say that on the rail, there is more dissipation than in the metro case. Knowing the voltage and the current on the rheostat, it has been possible to measure the resistance, to evaluate the resistance. Here is reported the evaluation of that quantity during a typical break, the top figure, and during an intensive break, of course recorded in Bardonecchia again. This is the second one is a 4-minute break. On the right side, we have a statistic evaluation of that quantity. We choose Susa Torino track because we have many journeys on that track. It can be seen that the mean value of RA is 1.52 ohm, and the variation with the temperature remains limited in a 3% range. What we can see about the braking energy. The braking energy varies greatly depending on the route, of course. During Bardonecchia Torino, for example, we have the maximum amount of braking energy that is really high compared with the other route. Note that the dissipated share is about 40% of the total braking on average. With this other representation, representing this way, it can be better appreciated the dissipated share and the variability of this quantity. That depends, as we will see in the next later, mainly on the number of trains. Instead, here we have the energy flow, the average energy flow for the metro case. You can see that almost 10% of the braking energy is dissipated on the rheostats. The chopper should dissipate the braking energy. We said that the chopper should dissipate the braking energy. Sometimes it has an undesired behavior. On the left, it is reported a braking event recorded in Turin, and on the right, we have similar behavior registered in Madrid. As you can see in both, we have a positive current at the pantograph during braking. In particular, it reaches almost 54 ampere in the rail and more than 21 ampere in the metro case. This happens quite frequently, around 6% of braking event in Madrid, and really route dependent in Italy. The chopper wastes some energy that doesn't come from dynamic brake. This undesired behavior is probably due to the high voltage level at the pantograph. A possible solution could be to control not only the threshold voltage level after the filter, but also the direction of the current, the sign of current in addition. Metro de Madrid has installed a reversible substation, reversible converter, DC-AC converter in the substation of La Moraleja in the middle of the line 10B. It can be worth pointing out that the reversible substation is in experimental stage and does not work at full capacity because of the limits of the amount of energy that can be transferred to the main grid imposed by the energy provider. Despite this limitation, we can compare the days in which the CDC converter is operating with those when it is not. This is a statistical analysis of ratio between dissipated energy and total energy for each breaking. Comparing the results obtained in conventional condition with those in reversible, it can be observed that there is a reduction in the dissipated share on the total that can be appreciated on both the mean that decreases of 2% and the 95 percentile that decreases of 4.3%. But if we make the same evaluation considering only the data recorded when there is a low number of trains contemporary in service, this difference became more evident. First of all, it is confirmed that that the number of trains has big impact on the line receptivity. In fact, we see that the mean dissipated share rise to almost 22% in this condition. Moreover, in this condition, the impact of the reversible converter considerably increased. This slide shows some scatter chart of the dissipated share with respect to the voltage level during the breaking. Each dot on the chart represents a breaking event. We have distinguished the moment in which we have the conventional substation and reversible and low number of train versus high number of train. But it is quite difficult to compare this chart. For this reason, we implement an exponential interpolation to simplify the comparison, even if the interpolation is not a good representation of the data because the data are quite scattered. The curve is an approximated relationship between dissipated share and the voltage level. As it can be seen, the curves confirms the impact of the reversible substation in both cases, despite the power limitation. In conclusion, we have seen that we can say that the energy dissipated, the breaking energy dissipated is the 7.9% of the total absorbed in the rail and 6.43 for the metro. The experimental result of the measurement campaigns could be used to foster the energy efficiency, to improve the operation of the railway systems, and to design dimensioning and positioning of storage system, for example, or reversible converter. Thank you very much. With this, I finished. I have concluded.
Thank you. Thank you very much, Antonio, for the interesting activity performed in Metro de Madrid and also in the railway system. You analyzed a lot of data. And,
a lot of data.
A lot of terabytes of data that we have. I suggest, first of all, I ask to the audience if is there any question. Okay, no question. I will have some consideration. I have some considerations, but I prefer to move this consideration in the final debate. So I give the floor to Giuseppe Graber from Hitachi Rail Italy. he will present a speech on how to recover the braking
Domenico, wait a moment. There is a question.
Ah, sorry. Good. From
I see
Luigi.
the chat.
Luigi?
Can you hear me now?
Yes, perfectly.
Yes.
Thank you very much. Thank you very much. Thank you for your interesting presentation. I want to give some contribution on the point of view of a train manufacturer. Of course, measuring is a quite difficult job. Also, train design is not a so easy job. So I would like to add some contribution about rheostat dimension. Please consider that dimensioning of rheostat cannot be made just on some measurement made in some condition and on some lines. Please consider that the presence of rheostat allows having electrical braking in any condition of train, and though not being really a safety topic, ensuring a train to have electric braking is very important, because electric braking is more powerful and more modulated than mechanical one, and moreover it allows having less maintenance costs. So the mentioning of the rheostat is made on maximum possible electric braking energy, and not on some, cannot be considered as over-dimensioned, considering just some measurement. Moreover, about absorption of energy from the line in the condition of braking, please consider that braking action depends on voltage, on actual voltage on the line. The entire network, the full network of trains is considered as a cluster, and it can also happen that a train breaks when that a braking chopper operates as the train is not braking, because perhaps there is some other train braking in the nearby, and so the braking chopper of the trains operates.
Yes, we experienced, we saw this last behavior of the braking wheels.
Yes, in particular in Madrid, the current is coming from another train, probably.
Yeah, so it's not. It is an important feature in order to allow the system to work, not something to correct.
Yes, but we want to put we want to point out that the voltage level probably is too high, and for this reason probably the chopper overwork.
The voltage level depends on the overall condition of the line, how many trains are braking, how many, and so on. Cannot, so it is a balance between among many different factors.
Okay. Yes, in the metro case is exactly so. In Italy, we experience, in particular, on a recent measurement that I have not presented, but probably Domenico has shown something about this. In particular, in this period, in which there are a low number of trains because of the pandemic, we have high level of voltage and very frequent phenomena like this shown, like those that shown in the slide, because of the high level of voltage.
It is not because of high level of voltage, because the system is dimensioned on an higher power absorption than it is in this moment.
Yes.
Yes. Thank you.
Domenico, I'd like to add a comment, very brief,
Yes.
but I think that it's crazy that one train regenerate energy, so inject energy in the system, and a different train dissipate that energy. I think that the control strategy should be improved, because if a train can successfully inject energy, that energy could be useful for other train. This is a not well coordinated system. If one train success in injecting energy and another train dissipated that.
I'm sorry, but please consider that first of all, it is safety of the system. What is really the master signal is voltage. Any operation has to be done in order to prevent voltage overcoming a safe level. So it is correct that a train operates braking chopper anytime it measure a higher voltage than it is going a voltage which is approaching limits. It is a kind of distributed logic among the whole fleet in order to avoid that in any point of the net voltage becomes too high. And it is not so easy to see what is crazy and what is wise.
Okay, I think that the point of view from train manufacturer is fundamental. No, I want to highlight that we provide. Our aim is to provide methodology to investigate the actual state of energy, but the analysis of the data, of course, is in charge of train manufacturer, of infrastructure manager, and so on. So thank you for this point of view. That is the important point of view.
Yes, of course we don't make train.
Yeah.
But I want to say a thing about the duty cycle statistic. I want to point that there are events at 50%, of course. There are events in which the rheostat works at nominal level. I don't want, probably my slide or my sentence generate
Antonio,
some.
Antonio, sorry. We have in the end of the session a debate on this that also involves new substations. So we can move this discussion in the end.
Perfect.
And I suggest to continue with the presentations. Next presentation is by from Hitachi Rail Italy. The title is how to recover the braking energy, a case study. So please, Giuseppe, take the floor.
Thank you, Domenico. Good afternoon. Can you hear me?
Yes,
very well.
Okay. Good afternoon. My name is Giuseppe Grabber. I'm with the R&D department of Hitachi Rail, the Italian company manufacturing rolling stock within the Hitachi Group.
You have to take the control.
Yes, but I cannot move the...
To move the go on view. Okay, okay. Now you can use arrows and move.
Okay, okay.
Okay.
Thank you. This is an overview of my presentation. I will talk about energy efficiency in rolling stock from both point of view, rolling stock manufacturer and the customers. I will discuss, I will introduce the contribution of Hitachi Rail to MyRailS project. I will introduce some elaboration of data acquired on Metro de Madrid test runs, and I will propose a case study for use energy storage system to recover braking energy. More and more customers' requests are related to energy efficiency for rolling stock. This is why, because the energy efficiency is very important within the life cycle cost. In particular, we can see that the major drivers are the energy consumption and the maintenance cost. So, for these reasons, Hitachi Rail's Hitachi Rail's products are related to reduce the energy consumption of vehicles and to increase the reliability and availability of their products, their rolling stocks. In other words, we will reduce the low life cycle cost. In this picture, in this slide, we can see an example of this. This is a call for tender, a customer call for tender for the latest, one of the latest vehicle, the Rock, the regional train product of Hitachi Rail. In particular, you can see that one of the requirements, the technical requirements, are related to the energy efficiency, and there are many technical requirements, but energy efficiency is characterized by a relative high score. In fact, this score is 2 over 100% of the total available score. So, with this in mind, to obtain high level of energy efficiency, we need to compare different solutions. To compare different solutions, we need to perform accurate measurements. In particular, for improve energy efficiency, are required measurements related to loss reduction of losses, measurement related to the energy absorbed by the train in order to reduce the cost, measurement related to auxiliary systems in order to compare different HVAC technologies or different lighting systems and so on. And finally, to compare different energy management strategies. Eco-driving system, for example, as it was said in the previous presentation, and for evaluate the performance of energy storage systems. For these reasons, Hitachi Rail participated to MyRailS project, and it has been involved in several activities, in particular related to measure the energy dissipated by the braking rheostat. In particular, Hitachi Rail acquired and studied current and voltage waveforms on different railway vehicles of its own production. In this slide, we can see that the rheostat current is produced by the braking chopper, that it is a power switching converter, a switching power converter, and you can see that it is very the harmonic content is very high, and so it is not easy to evaluate the power dissipated by the rheostat. For the test measurements, the choice of the metro vehicles of Metro de Madrid comes from the fact that Metro de Madrid and Hitachi Rails are the end user and designed the manufacturer of this rolling stock. So it is a good, it was a good choice for the project. Hitachi Rail elaborated and used the model of the rheostat and the braking chopper and its control algorithm in order to design the traction, measurement chain and validate the measurement. In particular, the electrothermal model is useful to validate the measurement of the temperature measurement related to the power, the estimated power of the rheostat. In this picture, we can see the electric schematic of the traction chain of Metro de Madrid and where the transducer were installed. In particular, the transducer were installed by taking into account reliability of the measure since the long time where the measurement, the test measurement lasts, and the availability of the system and the measurement chain. Acquisition results were obtained by the Metro de Madrid line 10B since the 2019, and in particular, the accurate measurement system installed in Metro de Madrid has used also to validate the traction control unit signals and energy measurement implemented on board. In particular, in this picture, we can see the, for example, the pantograph current. The red one is the current acquired by the traction control unit of the vehicle, and the blue one, overlapped by the red one, is the waveform current acquired by the accurate measurement system installed as part of the activity of the MyRailS project. Before to show some elaboration data of the, related to Metro de Madrid test runs, it's important to remind the TechRec standard. According to that, we have to design the braking chopper according to the full rheostatic power in order to allow the vehicle to use the electric braking in all operating conditions, and so and then on all the possible track where it is when it can run. However, in real operating condition, we do not have only fully regenerative braking or fully rheostatic braking. So, in fact, if we analyze data acquired during the acquisition on the test track, we can see that the percentage of rheostatic braking, of the energy rheostatic braking, is on average about 77%. On the contrary, if we compare data acquired on the Metro de Madrid line 10B during the normal operating condition, we can see that the percentage of rheostatic energy is between 10 and 15%. So, with this in mind, it is important to evaluate the braking energy that we can recover in order to decide if it is useful to recover this energy or not. In particular, if we have a relevant part of braking energy that can be dissipated by the rheostat, could be interesting to use onboard energy storage systems in order to recover this energy and reuse then during the next acceleration phase or for auxiliary loads. In particular, there are different technology commercially available at the moment. And Hitachi Rail used for one of these products ultracapacitor based onboard energy storage system. This is why because it is much effective in application where it is required a high peak power, specific power, and the recovered energy is lower than a few kilowatt hour. Why in particular, why ultracapacitor? Because supercapacitor are electrostatic devices with very high capacity value. And unlike batteries, they not require chemical reactions. So so they are characterized by very good dynamics in terms of power density. This characteristic can be seen on the Dragone chart on this picture, and ultracapacitor are characterized by very high energy efficiency, and moreover, the life cycle of this device is very high. In particular, we can estimate about 500,000 cycles of discharging cycles for these devices. In this picture, we can see one of the used commercially available ultracapacitor modules. And in this picture are also reported their characteristics. Now, in this slide, we can discuss the sizing, the preliminary sizing of an energy storage system based on ultracapacitor. If we consider one first sizing target of 1.5 kilowatt hour of energy that could be recovered, that is a medium point between the situation on the line 10B of Metro de Madrid, a very efficient line where the energy where the braking energy could be injected in line without problems, and the situation of the test track where we have practically a fully rheostatic braking. So by using a module such by using the ultracapacitor module such as the one showed in the previous slide, we need 15 ultracapacitor and 900 kilograms of weight for implement the onboard energy storage system. If we have a problem on about the weight of the energy storage system, and we would like to reduce this weight, we can for a particular rolling stock, we can set the sizing target to 1 kilowatt hour. By using the second side target, we need 10 ultracapacitor, and the total weight is of about 600 kilograms. This is the implementation of the system. Hitachi Rail implemented this system on Metro Bergamo, for example, and we can see that we use 2 branch of 5 ultracapacitor modules commercially available, and Hitachi Rail designed and implemented the protection and control circuit for OBES, for the OBES, the DC-DC power converter, and the protection and control circuits for the DC-DC converter. Okay, the conclusions. The energy efficiency is one of the most important requests by customers of rolling stock. So in this project, we measure the energy flow during of the vehicles, and we highlight that in the braking energy and the rheostatic energy strongly depends by the operating conditions. In particular, if the braking and the rheostatic energy is a relevant part of the braking energy, it could be useful to recover this energy, and we can use energy storage systems, onboard energy storage systems. one of the most suitable technology to implement the energy storage system are ultracapacitor due to their higher power density, their higher efficiency, and their higher number of charging and discharging cycles. Thank you for your attention.
Thank you very much, Giuseppe, for this very interesting speech. I can say that is an example on how to exploit data collected during the MyRailS measurement campaigns. So I ask to the audience if is there any question. I also remember that we can have a debate in the end. Let me check if is there any question. I have some questions, but I would like to use this to have this question in the end. So I think I don't see any question. I think we can move on the last presentation of the workshop. The speech from Daniele Gallo, Università della Campania, Luigi Vanvitelli, and the presentation design of an energy recovering system in the substation. So I like this aspect, 2 points of view. I have energy to recover, I recover the energy on board train, or I recover energy in the substation. Please, Daniele.
Thank you, Domenico. This is another way to use the huge amount of data that we have acquired during the measurement campaign. So, in fact, I try to show you a methodology to use the real field data for sizing and fixed position storage system. We focus the attention on a specific route. We analyzed the Rimini-Bologna, and we considered a round trip. So we take 2 journeys from Rimini to Bologna and from Bologna to Rimini. The considered train is a 464 with SIR carriage, and the length of route is 115 kilometers, covered with an hour and a half. This route requires a quite big amount of energy. A round trip is about 3.4 megawatt hour, and the injected energy just 18 kilowatt hour. So the dissipated braking energy instead was more than 400 kilowatt hours. Probably this is a very particular condition related with the low number of trains due to pandemic restriction. Anyway, is a good test case for showing our approach. We have only 4% of recovered energy, and so a huge amount of wasted energy. We monitoring this train, analyzing all the energy flow and together with its position. So we know exactly during its journey where the train, for instance, breaks. And we have measured the amount of energy breaks. Here you see the route from Rimini to Riccione. From Riccione to Bologna Centrale. And as you can see, just approaching to different stations, the train started the braking stage. If we see the opposite route, Obviously, you see the braking effort on your right because of the different train direction. So we know exactly where the train brakes, and we can evaluate how much energy in different points of the route is available for regeneration, available for recovery. Let's focus on a braking to start to obtain some number. This is the braking just before for release station, and here we can see that we have to manage a peak power of about 2.5 megawatts that last for few tenths of seconds, and amount of energy of each of these pulse of power are few tenths of kilowatt hour. So these are important numbers to choose the proper technology. I don't want to go in exact choice of what kind of storage system we can use. I just want to point out what is the number that you have to take into account. Real data taken from the field. Okay, now let's show in a simple way how recovering in a fixed position works. During the braking, the train is able to inject energy. If we have a storage system somewhere in the line, this energy could be stored. Obviously, along the path, due to the resistive parameter of the line, some energy is wasted. And obviously, if we change the recovery system position, we change the amount of energy wasted, but also the amount of energy saved. There is an optimization problem. What is the best position to collect the maximum amount of energy? To tackle this optimization problem, we adopt a very simple model. We consider the train as a simply power source, inject power in a certain point of the line, and we know exactly where you want to inject power and how much power you want to inject because of the experimental data. We model the line and the railway tracks from the point of braking to the storage system location as a simple resistance that varies with the distance, and we considered an ideal storage system. We have to add two very important parameters for this model: the voltage of substation where the storage system is located, and the voltage at the pantograph. It's important because for safety reason, the voltage at the pantograph is the train during braking try to rise this voltage, but for safety reason this must be limited, so there is a maximum increment that is allowable. As for voltage in substation, we started the whole analysis considering considering the average value that was measured on this line, 3,700 volt. Okay, starting from this model, we can move the position of our storage system, and we analyze the amount of energy that can be saved. Okay, for the considered case, the winner is Imola. Imola is the best place to recover energy considering this route. Anyway, as we have a model, we can also imagine some modification in the situation. We considered the average value of voltage that we have measured, but we can imagine that is possible a voltage reduction, and we can see how the situation will change. Anyway, I want to first point out that we start from an initial condition with only 4% of recovering, and in this case we reach the 44% of recovering. If we, as I say before, reduce the voltage, obviously the amount of recoverable energy increases. For different value of voltage, we obtain different amount of energy, and the maximum of energy that could be recovered increases over more than 100 kilowatt hours. And if you note, the maximum point now is in Forlì. The maximum point is slightly move. So we, for the following of the analysis, we consider the Forlì as the best position for a storage system, and we keep on conduct our analysis. I propose to reduce the voltage of the line, but this directly impact on dissipation during traction, because reducing the voltage increases the amount of current, and so the dissipation during the traction stage. So to properly evaluate if this voltage reduction could be a useful approach, we evaluate always with a simple model what are the dissipation related with the traction, and we can analyze the increase of dissipation related with the reduction of the voltage. Okay, for this model, we take also in this case a simple model with the resistance in substation and for the path of catenary and railway tracks, and we consider a parallel of the substation in supplying the train in different position. From this analysis, we found that for a voltage that is close to the actual voltage of the line, we recovered the total amount of 185 kilowatt hour. We dissipated while recovering this energy 7 kilowatt hour. So the energy that arrived at the storage system is 178. The dissipated energy in the traction is at all 87 kilowatt hour. So the net amount of energy in this situation is 92 kilowatt hour. I want to underline that this is dissipation in traction is not due to the storage system. This is the dissipation for all the traction stages. So, in fact, without the storage system, we obtained almost the same amount of storage of dissipated energy, 86 kilowatt-hour. Now we can compare the increase of dissipation, reducing the amount of voltage. As you can see, of course, the dissipated energy increases, and also remarkably. Anyway, for a proper comparison, we have to look at net saved energy. Also, the net saved energy increases, reaching a maximum value of 172 kilowatt-hour for a voltage of about 3,300 volt. So we choose this voltage as target voltage, and we keep on our analysis. We have to face first a look to final energy balance. We start from 4% of injected energy, and we lost 96% of energy, and we finally arrive in the optimum position with optimal level of voltage to recover 67% of energy. The bad news that 33% of energy is impossible to recover. Also, with an optimized situation, this amount of energy is not recovered and is wasted. Obviously, not injected energy reach the storage system, but we have already talked about this aspect. Okay, last question that we have to answer is the storage system sizing. Storage system sizing, we evaluate the total amount of saved energy, but obviously we have not to store all the energy at the same time. The storage system is charged during braking, and when the train starts in following traction phase, discharged. The actual size of the storage system could be much smaller than the total amount of saved energy. For the management of energy stored in the system, we account of two different strategies. The first strategy use the energy stored in the recovery system with high priority. So this facilitate the discharging of the storage system. The second strategy, instead, the storage system is in concurrence with other supply system. So has much more difficulty in discharging, because in competition with other source of energy, and while the train moves away, are closer to the train. Okay, the result adopting the first strategy is this. We see that this is the amount of energy accumulated in storage system while the train move away. So the peak value of storage required is 25 kilowatt-hour. This kind of strategy to have allows to have a storage system often empty. And this is useful because we considered only one train in this simulation, but obviously in real situation we have more than one train. If you want to adopt a not prioritize the usage of the energy stored, obviously the average value stored in the system increases. The system has difficulty in discharging, full discharging, and in this case the energy stored is double. We need a double of amount of size for in this case. So we presented a methodology to exploit the experimental data that are collected in the measurement campaign performed during MyRailS project, and we presented a simple design approach for energy storage in a fixed position. The system was optimized in terms of location and in terms of voltage, accounting the losses. The methodology obviously could be further developed, considering a more complex model, the presence of different trains at the same time. With the timetable, we can move different trains on the tracks and see what is the energy flow in this situation. And we adopting some scaling factor. We analyze a specific train. Adopting a scaling factor, we can analyze, we take in account also different kind of trains. That's all for me. Thank you for your attention.
Thank you. Thank you, Daniele, very much for this exhaustive presentation regarding to the design of the storage system in substation. I suggest to present just in few slides the debate and then collect questions from the audience inside the debate. So as to upload the last. Okay, the last slides. After these presentations regarding where is the energy that can be saved and how we can save the energy, I like this priority stated by C. Senelec in the standardization on non-conventional DC substations. And we can also deal with future research activities. You can see in the slide where has been published and detailed this priority. I have to take the control, but we have just a couple of slides. Okay. The presented results related with the energy dissipated by the breaking rheostat and the effectiveness of new non-conventional substation highlighted the need of a new and smart management of the energy flows and of the supply voltage level. New standardization actions can allow the design of innovative and efficient railway and metro supply system, and is welcome. For example, the trigger threshold of the breaking rheostat is too close. This is my conclusion. Is too close to the actual voltage level we have experienced both on board in railway and in metro systems. This condition can make useless the upgrade of substation, because if you have a train far from the substation, since the high voltage level, instead of delivering the energy to the substation, you waste on the breaking rheostat. The increased interest on the energy efficiency requires a wide monitoring in order to understand the real energy state, in order to optimize the whole system. And here there is let me say, the topic we have already discussed with the interesting point of view from Luigi Fratelli. So I ask a question from audience or comments. I have some comment, but I wait for, let me check if there is some raised hand. Okay, if not, I have a question I would to involve in the debate. Okay, sorry. Because before I laughed. Why I laugh? Because on my side, first of all, you have to know that the Forlì substation is now, sorry, upgrading. It will be installed a stack of a supercapacitor to storage the energy. But who decide that in Forlì station a storage system has to be installed? It's here. It's Engineer Carillo. So we can ask him why Forlì and not Imola. You have to switch on the microphone. Devi accendere il microfono.
Ma questo è un aneddoto.
Devi accendere il microfono.
È un aneddoto, quindi non c'ha niente di scientifico e niente di...
Deterministico. Professor Gallo, quando è nata l'idea 5 anni fa, ed ero ancora in servizio, ero direttore
the idea came up, I didn't have my role yet, but the decision was based on the fact that the station had spaces available, and this is why Forlì was chosen, on top of the fact that the staff was available, and also because I live in Forlì.
Thank you. Just if we have just a few minutes, and then we stop. A question for Luigi Fratelli, if you is here. The question is this: when a braking chopper has to be designed, which is the voltage taken to design the braking rheostat? 1.5, 1,500. You can.
Can you hear me?
Yes, now yes.
Okay, yes, thank you. You can assume it is a maximum in voltage levels are defined by normatives. There is normative saying what are normal operating voltage levels, the nominal one, the maximum and minimum voltage which allow full operation, minimum voltage which require operating at reduced power, a maximum voltage which is the limit for shutting the inverter, the converter on board, in order to protect the system. Please consider that voltage value is not a constant along the line, but it is an actual function of the distance from the substation. So what is really relevant is the voltage level at the pantograph of train. So you can consider that roughly the rheostat is dimensioned for the maximum operating voltage level at pantograph. You assume that voltage increases during braking as it is lower than nearly, as it is lower than braking voltage. There is a braking voltage which is near to maximum operating voltage, and as it reaches such values, train starts braking in order to avoid further increase of
yes,
voltage.
yes.
So you can consider the actual power divided by such voltage.
Yes, yes.
Squared, of course.
You mentioned the standard. So since during our monitoring, several days, several weeks, in which we never experience, for example, or almost never experience 1.5 kilovolt, maybe it means that you have to think about to, let me say, remodulate the standard value, because we go to design something considering conditions we are not present in fact in field. This is just a consideration.
I can understand the point. Please consider that it is normal that that the voltage is quite high at substation. Dr. Carillo will for sure confirm it. It is usual, it is 3.6 or 3.7, sometimes also 4,000. Please consider that during the life of a railway infrastructure, traffic increased and increased very of a large extent. And initially dimensioned the catenary and infrastructure has to cope with increased traffic. And so in order to cope with such large request of power, the simplest operation is to rise voltage in order to limit current, to not to increase too much current, and not to have large voltage variation at pantograph.
Yes, yes, good point. Thank you very much for this debate. We are in the end of the workshop. I think it has been a very interesting, exciting contribution, and I hope that stakeholders found interesting point for their activities in developing the research and so on. Let me thank, first of all, Engineer Carillo for having moderating the workshop. Let me thank my family, otherwise I cannot come back home. Let me thank in particular Silvia Cavallero for her support in organizing the communication of MyRailS project and for this workshop. We had a very strong impact, I think, on stakeholders. And let me thank, of course, all the partners who are involved in the project. And finally, Università della Campania and Daniele Gallo's group, because of their activities, strong activities in arranging the setup and analyzing the data. Thank you. Thank you very much. Bye-bye.
Thank you, Domenico. Bye-bye.
Thank you. Thank you.
Thank you. Bye-bye.
Thank you.
Ciao.
It was a
Bye-bye.
pleasure.
Bye-bye, everyone.
Bye.
Bye. Ciao. Bye-bye.
Thank you for the workshop. It works very well all the time. Thank you for
Thank
all.
you. Thank you to the
Thank you,
video
Daniela.
maker. Thank you to
I
the
am waiting
video
for the
director.
link to see the workshop, the video of in RIM and FFII.
Yes, yes, for sure.
Thank you all.
Thank you.
Thank
Thank
you
you
so
very
much.
much.
Bye bye.
Thank you.
Bye.
Bye. Bye-bye.